Hi, Chris. Thank you, Chris, for the organization of this demo event. This morning, I told about suppression difficulty and the evaluation of this index in Central Europe. Suppression difficulty index combine variable related to fire behavior and variable related to suppression operation. We have a potential fire behavior in one pilot site, in one area, in one fire, and it's possible to have different control opportunities such as fuel model change or the presence of road or way. We can reduce the fire risk, and we can have more opportunity to control or the probability to control the forest fire. The suppression difficulty index is a equation, has different components, but to resume, it's important to understand two parts of the equation. In the upper part of the equation, the numerator is related to energy behavior parameters, and the denominators is based or depend on suppression opportunities. In the first case, the energy components depend on two variables, flame length and head per unit area. In the case of the denominators, has four components: accessibility, mobility, penetrability, and fire light openings. We have the equation is very complex, but I think the most important is understand the components of the numerator and the denominator of the equation in the two kinds of variables that compose this index. The origin of the suppression difficulty index is in this paper. This paper is created by Unis Forest Service and University of Córdoba in Spain. And you can see on your right have the final products of the Unis State Forest Service. It's based on meteorological percentage, but we have other kind of product of final cartography. This is the cartography of the suppression difficult index in one demonstration area in the south of Spain, in Andalusia. This is different for this previous because in this demonstration area is dynamics. In this case, it's statics. You can see the meteorological condition for the next 3 days. You can select the day, and you can change the hours of the day to see the difference between between the night or the day or the different hours of the day. This is more dynamic and is very useful for the fire manager in this demonstration area. In the following slide, you can see one fire. We can use two fires to evaluate the suppression difficulty index. In this case, you can see the possibilities or the control opportunities of this real fire. You can see fuel model change in this area, this area, in this area, and you can see the possibility to control line with the presence of road, in this case, the accessibility. These components are in the denominator of the equation, in the suppression opportunities. You can see other conditions that affect the numerator of the equation, the presence of small canyons. You can see this one here, and higher fuel continuity in the south of the fire, the southwest of the fire. We have two options to calculate the suppression difficulty index in this real fire. On your left hand, you can see the fire risk cartography. You can see in the west side. And on your right hand, you can see other different cartography that is created by real meteorological condition of the day of the fire occurs. You can see difference in the suppression difficulty in the level, very low. You can see red color in this area, and you cannot see in the fire risk products. It's the difference between use a static cartography or dynamic cartography. The evaluation. The evaluation of the fire risk cartography, and remember, fire risk cartography in this case, suppression difficulty index is based on the products of the projects, and is a status in this case. It's lane that is calculated by other tasks of the project. This is for the perimeter of the one fire, the first fire. You can see the color, the different levels of the fire, the suppression difficulty. I remember the topography and the opportunities or fire opportunities of the fire. And you can see the result in Google Earth. You can see the small level or the lower level of the suppression cartography coincide is related to the control line, to the perimeter of the fire. When I test the first fire, the first real fire with static cartography, because this is static cartography, it's not with real meteorological condition, you can see a very reliable result, because more than 88% of the control line fire perimeter is in very low or low suppression difficulty index. I think it's a very good result for a static cartography. The second one, when I test the products, it's very similar to the result of the first fire. You can see the difference between static product, static results, this one, and dynamic based on meteorological condition and real meteorological condition of the day that fire occurs. We use the statics, the real products of the project. You can see the result of this fire, and in this case, more than 89% of the control line fire perimeter is in very low or low suppression difficulty level. As conclusion, suppression difficulty in the result Central Europe, I think has very good results, have been quite promising, higher than 88% of the control line in both fires. However, we have careful, because it's necessary to test with a greater number of fire and condition, meteorological and I think topographical condition is required to reach a better result as preliminary result that we can see. And thank you for the opportunity to present these results.
Thank you, Jan. Quite interesting results there. We're ahead of time, which is very unusual for these sorts of events. Once again, I'd like to present Matthias, and Matthias is going to talk about the fuel mapping and the fuel behaviour from the fire from the area that Juan has just talked about there in Bohemian and Saxon Switzerland. So over to you, Matthias.
Yeah, thank you, Chris. So as part of Fire EU Risk, we also investigated the fires that occurred in the Bohemian and Saxon Switzerland national parks in 2022. It was a fire that caused a big attention, actually, also in the international media. You see here some screenshots from some international news websites. I think it got so much interest also internationally, because it was in a national park, which is a touristic destination of a very big value, and it was also the largest fires that occurred in the Czech Republic. As part of Fire EU Risk, we actually visited the burned area of this fire in October 2022, so just a couple of weeks after this fire. And I think it was quite impressive also for our project to see this area. So the fire occurred at the border between the Czech Republic and Germany in 2 national parks. So at this border on the Czech side, there is the Bohemian Switzerland National Park, and on the German side, there is the Saxon Switzerland National Park. The fire started in the night of the 24th of July. It spread over a period of 5 to 6 days till the 29th of July. But the firefighting operations still were ongoing for several weeks until the end of August 2022 on the German side. Around 1,000 hectares burned on the Czech side of the national park, and 113 hectares burned on the German side of the national park. Yeah, and it was the largest fire in the Czech Republic, and I think it was also the first time when the Czech Republic asked for help from the Copernicus Emergency Management Service and from the European Union civil protection mechanisms, at least for a forest fire. Only for the German side, the costs of this firefighting operations were around 11 million euros. Yeah, I don't have any number for the Czech side, but only for the relatively small burned area on the German side, it was 11 million euros. We wanted to investigate what kind of fuels did this fire affect and what was the fire severity of this fire. So Marine already introduced these different layers that we need when we want to, let's say, model fire behavior. And one of the key inputs is a map of fuel models or fuel types. Fuel types describes the type of plant materials that will likely burn during a fire. And then these fuel types are translated into fuel models to estimate with fire models like PlumMap the fire behavior. As part of Fire EU risk, there is a European-wide map of fuel models at 1 kilometer resolution available, and Marine also presented this fuel map that is available for the Central European pilot site. Here, for investigating this fire, we additionally created another fuel map on 10-meter resolution. The reason was, the topography of this landscape is quite complex. And this landscape, these both national parks were also affected by bark beetle infestations in the last years. And in our European fuel maps, there is not a class for, let's say, a disturbed forest. So we here made a fuel map that also includes disturbed forests. You see the map here of fuel types for both national park and landscape protection areas on the German side and on the Czech side. And what is specific about this map is that we also mapped the areas of disturbed land where bark beetle infestations occurred. And you see these areas are actually widespread over the national park regions. On this figure here on the top, you see the distribution of the fuel types within the burned area. And we did some statistics on this, and we actually also went to the field to map different fuel types. So we went for the first time in September 2022, so directly after the fire, and we also did a second more intensive field campaign in October 2023, where we visited 83 sites in both national parks to, let's say, classify the fuel types. And in 2022, we also mapped the fire severity in the field. Here you see the distribution of the burned area for the different fuel types. Most of the burned area occurred in places where bark beetle infestations occurred in the years before. But also, the fire affected actually several vegetation types. A large fraction of the burned area occurred also in areas where you have a high, let's say, presence of rocks and little shrubby vegetation. But what was also surprising is that this fire actually burned a quite big extent of beech forest, only in the understory. I mean, this was in the beech forest only a surface fire. But after the fire, we actually see a strong mortality of beech trees in these forest stands. And then also some pine forest stands were burned and some other forest stands. We also investigated the intensity of the fires. Therefore, we use satellite observations of fire radiative power, which gives you the energy emissions of a fire. And the disadvantage of this approach is that the resolution of these satellite observations is rather coarse, but it gives you a first idea of the intensity of the fire. And if you look here on the distribution of the fire radiative power in megawatts, you actually see the highest intensity of this fire was in areas that were bark beetle infested, so where we had actually a high accumulation of woody debris and also already ongoing regeneration of young vegetation. So from our analysis, we cannot really say what is causing this high intensity. It can be because of the presence of the woody debris, but it can be also because of the regeneration of young spruce trees in these stands. We also mapped the severity of this fire on the one hand in the field. So we went in different locations. These are the blue dots in the field where we assess the so-called composite burn index. And we also use satellite observations from before and after the fire to map the burn severity. And here you see the burn severity map. And if you look on the distribution of the burn severity, you actually see that most of the area had only moderate to low severity, and only small fractions of the burned area had a high severity. So I would say, for the people that were involved here in this region in fighting this fire, either from the fire rescue services or from the national parks, this was really an extreme event, and it was a severe fire. But if you quantify the severity of this fire with matrices like the normalized burn ratio or the composite burn index, it's only a moderate fire, and fires that occur, let's say, in the Mediterranean or in the United States, where these indices are usually applied to, they are much more severe. On here you see 3 examples of, let's say, how a moderate to low severity looks like in a more mixed forest stand. You see here a moderate severity in a forest stand that was previously affected by bark beetle infestations. And here you see a forest stand with moderate to high severity. What was also interesting, the National Park Administration had several wild cameras in the field, and actually one of these wild cameras also captured the fire and survived the fire. So here you see an image from before the fire, with a lot of regeneration ongoing in this previously disturbed forest stand. And then you see during the fire that the fire mostly spreads at the surface, but it also climbs up in the standing dead trees. And what you also see from this camera trap is actually that the regeneration of the young spruce trees caused for a short time a very high flame length and a high intensity. And after the fire, you see that most of the surface fuels are burned, especially the litter, the shrub layers, the regeneration of young trees is burned, the coarse woody debris, so the dead stems, they are burned at the surface, but only until a depth of a few millimeters. We then also use this fuel map to make a map of potential fire risk for this area. So we also used the flame map model to get information about flame length and burn probability, which you see the legend on the lower right side. So if you see here darker colors, it means the burn probability is quite high. And if you see more red or more purple colors, you see that the flame lengths can be very high. What is interesting is that the fire risk is higher at the east side of the river than on the west side of the river. And this can have 2 reasons. One reason is actually more tourists go to the east side and not to the west side. So there are more ignition points on the east side than on the west side. And another reason might be there are also more of disturbed forest stands on the east side than on the west side of the Elbe River. Yeah, you could also zoom into this map to explore the fire risk more at a local scale. You see here a village in the national park region, and what is actually quite surprising, you see the highest burn probability and flame lengths actually not in the forest stands around these villages, but more at the meadows, which actually means during very dry and hot summer conditions, if you have well-developed meadows that dry out, they can cause a very fast spread of the fires with high flame lengths that then can burn into the forest stands. So yeah, I think what we need to add here to the public debate about the role of the deadwood in these forest stands is not only the deadwood is important, but actually, if we want to protect the villages, we also need to consider how we manage the grasslands around the villages. Okay, so in summary, we created a cross-border fuel classification for this region. The validation of this map is still ongoing and we try to improve it. But what we see as, I would say, robust results from our analysis is that in the disturbed forest stands, we get higher char heights and more torching. We get more intense fires, and we also get higher burn severity in this fire in 2022. And well, this fire was burning from one country into another country, which means, which you see, fires don't need passports. So that means if we want to manage fires in Central Europe, we actually need to use the same approaches of fire risk assessment and fire risk management in neighboring countries. I think one lesson learned from this fire is also that the communication between the emergency services, between the regional administrations in the neighboring countries needs to be improved in case of such emergencies. Okay, thank you for your attention. And again, if you have questions, you can ask in the questions and answer section.
Okay, thank you, Matthias. And we are on time. So it's now 10:45, and we're going to have a short break, and we'll resume again at 11:10.
Could you see the presentation?
Yes, that's
Okay,
perfect.
perfect.
Thank you. Perfect.
Thank you,
Over
Chris,
to you.
for the introduction. My name is Pere Gelabert, and I am one of the researchers of the University of Lleida involved in the fire risk project. Well, today I'm here to explain how we proceed to obtain the human-caused ignition probability map. Well, our product is framed in danger wildfire risk component, specifically in the human ignition section. Okay, this is only to frame our work. And well, to carry out the modeling process, we obtain the fire data ignition points by means of different fire colleagues that are in contact with institutions. We collect a record of 1,600 fire ignitions, and we use that as a variable. As a predictor, we use the population density accessed from global human settlement layers from European Union. That is a raster at 100 meters spatial resolution. Distance to roads started from Globio, Global Road Inventory Project. Percentage of elder people extracted from Eurostat databases at municipal scale. Okay, distances to wildland agricultural interface, wildland urban interface, and wildland grassland interface derivated from core inland cover, and well, the percentage coverage for urban crops and forest areas, and the fuel types that are extracted from the product developed between Marin Bugarik and us. Okay, respect to the modeling approach, we apply a random forest binary classification model where we calculate the probability of B, the ignition category. To do so, we use the ignition points data that are collected by our colleagues, and we create a random sample with the same size to ignition datasets, and we label these new samples as no ignition points. Then we calibrated 100 models to account for the variability of to have an account the variability of the predictions, and as a result we present a map of the probability of human-caused fire ignitions occurrence, and also the coefficient of variation calculated across the 100 models. Okay, from the result session, we could affirm that we achieve a good model performance in our pilot site. Concretely in Europe, in Central Europe, we have a high area under receive operational curve. And the main factors that drives the human ignitions in Central Europe of pilot site are percentage of wildland, distance to wildland urban interface, distance to roads, and distance to wildland agricultural interface. The results suggest that in a general way, the northern pilot sites, wildland related variables have more driving power, and in the Mediterranean, and in the other hand, in the Mediterranean ones, demographic variables present more relevance. Okay, and to finish, here we show the spatial explicit output of human-caused ignition probability for Central Europe. And well, in this pilot site, we could see a marked difference between countries. This is mostly motivated by the effect of big socio-demographic differences between the three country members. Okay, and that's all from me, and thank you for your attention.
Okay, thank you, Juan. Could you stop sharing your screen? Yeah. And Juan, if you wouldn't mind, there's a question in the question and answers from Kazina regarding why the variable of people over 65 was used. If you wouldn't mind, would you perhaps give an explanation, please?
Why? Okay, we use
no. Sorry. Okay, so you have time. Go on.
I type the answer, or
yeah, you can talk now. We have a little bit of time if you'd like to explain.
We use this variable as a proxy of land abandonment, because elder people is in a retired period and could not cultivate or manage the land. Is a proxy of land abandonment.
Okay, thank you very much.
Welcome.
Okay. But perhaps Kazina might have a follow-up question, so if you wouldn't mind just staying hanging around for a bit, maybe answering if she has another question. Okay, thank you very much. So
thank you, Christopher.
Okay, next up we have Kirsten Thonica from the Potsdam Institute of Climate Change Impacts. Kirsten, over to you.
Hello. I share my screen. Very happy to be here. Part of the panelists to explain what we have been doing in the project. The topic of my talk is the future fire regimes, and and the simulations that we conducted with our model. So to explain, wait a sec, there's something. Yeah, here we go. A short overview. So I will quickly explain the methods that we use to simulate fire changes. In future, also using dynamic global vegetation models under future climate change and also land use change. I'll explain shortly how these scenarios will look like, and also possible changes in vegetation and fire in terms of fire weather, burnt area, and also changes in biomass as an example of the underlying changes. And also some maps how this looks like at the European scale. Okay, so what did we do? There are climate scenarios available from the global climate models, and also within the project, land use scenarios were developed. These work as input to our dynamic global vegetation model. This is called LPJ-ML. It's a dynamic global vegetation model that simulates natural vegetation as well as management of vegetation. So cropland and managed grassland are simulated. Managed trees, the carbon, the energy, and the water cycle are all captured because they all interact. And of course, fuel production, dryness is the precondition for fire, and this basic mechanism is also considered here in the fire model. We have a process-based fire model that takes into account lightning-caused ignitions, human-caused ignitions. It burns in natural vegetation. It can also be applied to managed grasslands. So under climate change, the proportion of natural vegetation might change. Climate change has an effect, and the net result will then be changes in burnt area. And this is what we were looking at in the project. So how did we arrive from the IPCC model archive to high resolution scenario data? This is the work from MeteoGrid, our colleagues in Spain. They took from a reanalysis data set, very quality controlled, the historic climate data for the European domain, which you see here in the map. And climate models have also some errors, and so they bias corrected them. And also because we want to have finer resolution to connect the different scales, we had a statistical downscaling methods applied to daily values and also 9x9 spatial resolution. So we are using a really fine grid. And these were produced for the fire risk European region, which you can see here, and also for the different pilot sites and demonstration areas. So what are the scenarios that were used? So there's a combination of climate warming simulated by the climate models, and in combination with narratives of future development in socioeconomics and in land use. You can combine these land use narratives like, for example, SSP1, sustainability, with some low climate change scenarios, but also a rather pessimistic scenario could be that the world regions are rivals and there's a lot of economic stress, and not so much the transformation to a green future. And that would result in a forcing of 6 to 7 watts per square meters. So it would mean that, for example, if we combine the so-called RCP 2.6 with the SSP1 sustainability scenario, we could reach the global goal of the Paris Climate Accord, reach the 2-degree target. With regional rivalry and intense land use, we would land in a 3 to 4 degree warmer world. And I will try to use this description to distinguish the different results. And because each climate model has slightly different model outcomes, these scenarios are simulated by these climate models. We selected the scenarios according to their ranking using the fire danger index, the FWI, which is widely known to few of you. So what does it look like if we plot it for the Central European pilot site? Here we have the precipitation map for the historic time period averaged as mean annual precipitation. And clearly you see the mountain ranges you are very familiar with, and also the more lowland areas receiving a bit less precipitation. If you have the combination of the SSP1 with the RCP 2.6, the Paris goal map, we see an increase in precipitation according to this scenario. We averaged this map over 5 climate models that we selected. Of course, behind that, there's a range, but they show an increase in the precipitation for both scenarios. And this is something important that we will have to keep in mind when we see the changes. For the future climate conditions, you will see that there is here the current distribution of the mean annual temperature with SSP1 Paris goal achievement. We have an increase in mean annual temperature, but it's still sort of okay in the mountain areas. Here you see the cool feature, but this is all vanishing in the 3 to 4 degree warmer world, where we have mean annual temperatures in these areas above 12 to 15 degrees, which is quite a substantial warming for the average. So these climate scenarios were then taken to apply the Canadian Fire Weather Index to see what the fire weather conditions would look like. And this is for the optimistic scenario applied for the European scale. So if you look at this map for the summer mean spanning the year 2000 to 2030, you have the picture of high fire risk in the Mediterranean and also in the Balkan countries, low to very low fire danger in Central Europe and in Scandinavia. Here are marked our pilot sites, and we will look into the pilot site of Central European, which is the topic of today. And so this is out of these climate variables, the calculated fire weather index. Again, the mountains are pretty good visible, low fire danger in the lowland area. But these are then the changes at the end of the century. If we check these different climate scenarios, the higher the number here, the more severe the climate change will be due to a rising CO2 concentrations in the atmosphere at the end of the century. So these differences might look pretty low because we end up in moderate fire weather conditions. But maybe looking at the absolute differences, you see a more marked difference that is consistent with the climate pattern that we saw in the temperature changes. So this is really a marked difference where the cooling effect in the mountains disappears increasingly. This is the trajectory that gives you an illustration about the different climate scenarios for the Central European pilot site. Also you see quite some variability in the small lines behind that picture. So how does that translate into changes in area burned that we simulated with our dynamic global vegetation model? Remember, here also the size of the natural vegetation is limited by land use, which we also considered here. So low average annual area burned might mean there's an urban center or a high proportion of land use. And so this is the picture that we simulate, and it's a direct translation of the fire risk. In the future, as we saw just now, also for the projection or spatial distribution of the human-caused ignitions, we have an increase also on the Paris gold mat scenario, that fire will increase. So we will have annually more between 20 and 30 hectares burned. This then increases even further because we are losing the cool climate in the mountains, and also area burned will be substantially higher also in the mountain areas. So what does this mean for the vegetation, or how is the vegetation changing at the same time with climate and land use change? Here we see a map of the simulated biomass within our 9x9 kilometer grid cell. So the dark bluish colors mean there's a high average biomass. We express it in carbon, but you can roughly multiply it by 2, then you have it expressed in biomass. Or multiplied by 3.6, then you can express it in CO2. Never mind. What we see is we have in the mountain areas high biomass, and also where we have a large proportion of forest area that is also high in biomass, where we have the urban centers and agriculture. We see low biomass because it's all covered up by agriculture and no standing forest. If you now move over to the change in biomass, we see a picture that we find surprising, and it is that under the scenario of rather moderate climate change, so the Paris goal is met, we see a decrease in vegetation carbon compared to the historic one, but there are some areas where vegetation is increasing. And here, under the really more intense 3 to 4 degree warmer world, we have an increase in biomass here and a decrease in the mountain areas. And this is something where you start scratching your head, because of course we have a temperature increase here, a substantial one. Precipitation remains the same and increases even more under future scenarios, but here the CO2 concentration is not that big, and this has an effect physiologically for the trees on saving a lot of water, which is it might be here the dominating effect. And here we have the impact of still temperature increases that can stress the vegetation. And so we might see a loss of biomass here. In both cases, we have an increase in area burned. Here is much more area burned. It will remove the dead fuel on the ground, and probably has a little effect on the standing vegetation. Remember, this is in both cases simulated potential natural vegetation. So no spruce or pine or monocultures are simulated, and we don't include bark beetle. So this is a combination of the climate changes and the different physiological responses that lead to these unexpected results for this region. What does it look like at the European scale? Again, going back to the future fire weather, we have here again the historic time period, and from that for the different scenarios. We have an increase. We see an increase in the annual summer fire weather index. So it's the mean from June to September. And so if no climate protection functions at all, we have a drastic increase in the fire weather index. And it levels down only if we meet the Paris Accord, the 2-degree target. This is now average for the entire region in Europe, the domain that I showed you at the beginning. And it looks, the picture, how the different scenarios stratify, looks similar to the pilot site for Central Europe. I would like to draw your attention also to the changes in seasonality, is that with these projections for each month, you also see an increase in variability, and also an extension of the fire season, increasing fire risk in September, but also in October compared to the historical, where you see the small box plot here in black. And so we have stark increases in the distribution, the worse climate change gets. And this jump is mostly pronounced in September and also in October with the distribution. So what we will see now is the results for the European scale for the sustainable Paris goal met low warming scenario and not so sustainable medium warming. So these are the changes in temperatures for the two scenarios as plotted as differences. Here are the differences in the precipitation and as expressed as a relative change. And here also there are some changes in the land use. So when you see some pattern in the green color, we see that there's also the proportion of natural land is increasing. And so here we also see that it is expected that quite some agriculture area and pastures will be abandoned. So that also increases the potential area burned, and might also increase to the fact that biomass is increasing. It is more pronounced here in Romania and in the Balkan mountains, and also some other smaller regions expect an increase in natural land. So the potential area that can burn can increase. It is less so of a pattern, but at a smaller scale, spatially more fine in this not sustainable warming, because we assume that intensive land use will continue. So then the question is, what are the changes in the burned area at this scale? So here we plotted the changes as relative changes. So areas that are in gray mean that for the historic time period, there was no fire simulated, which is clear for most of the Scandinavian regions, and also for the British Isles, and some very wet areas in Atlantic Europe, and also in some mountain areas or high agriculture areas, like here in the Po Delta, in Italy, the same as here in the high intensive agriculture areas in Germany, the Benelux, and also here. And of course, you also see urban areas being marked here, of course, because there people live and there's no natural vegetation. So, and then we classified the changes in burnt area. And where you have these light colors, you have rather the same burnt area compared to the historic time. And here you have higher burnt area increasing by 50 to 300% or even much more. And the same with the reduction and much less area burned. What do we find here is that we see with the Paris Gold Mat, still an increase in area burned with 50 to 300% increases in the areas that are covered by forests throughout Europe. And we find areas in high elevation areas because of the strong warming surrounding the Alps, for example, but and the Balkan, Carpathian Mountains, but also in Poland and in the Baltic countries. And we see an interesting pattern is that here there is less area burned, and this is applying to the Iberian Peninsula. And this is in a large area where there's no changes, so fire regimes might remain as they are now. And so this can mean that it's happening for several reasons. We saw that the potential area burned due to land abandonment is increasing. But this is due to the fact that because of the changing growing conditions, we see an increase in tree cover, and this slows down fire spread in the models, despite having more biomass to burn. And so we think it's a combination of these vegetation changes with some changing in this CO2 fertilization effect. But then here with the strong warming and stark precipitation loss in the 3 to 4 degree warmer world, this area shrinks. So we have an increase in area burned, and the area where the area burned is smaller than today is largely reduced. And here the area for most of Central Europe, the Balkan countries, and also moving into southern Scandinavia and Finland here, we have a stark increase in area burned, increasing by more than 300%. And so to conclude, I've been fast. Okay, so the future fire situation in Europe will depend on the success of global climate policy. So we see, depending on the storylines, we see a stark difference in the two, depending on the climate scenarios, on what we get in terms of area burn, but also accompanied vegetation changes. The pathway, Paris Gold Mat, or living in a 3 to 4 degree warmer world, this will decide about the intensity of changes in vegetation and fire in the future climate. Sorry for this spelling error. In Europe, it means future fire weather will increase. The fire season will expand. And also there will be more extremes. So it's really up to us to decide which future. For Central Europe, the future burnt area is a result of multiple changes happening at the same time. Rising temperatures and this rising atmospheric CO2 on the way enhance the growing conditions of the tree with rising temperatures, and at the same time weather conditions, they can grow better. We see an increase in vegetation growth, but with lower CO2 we see a loss in vegetation. But in the 3 to 4 degree warmer world, there is a stark increase in vegetation because of this combination of physiology and climate. At the same time, we see an increase in fire weather. So, and also we simulated an increase in potential burnt area. but obviously this seems to be still at a rather small scale for Central Europe, which means that the vegetation is able to cope with that, and a reduction in land use will additionally increase forest cover that could burn. There seems to be something lost here. I'm very sorry for this, but maybe there was must have been a mistake in saving the file. Sorry for that. But it obviously means to say increases in forest cover that could burn. And so we can state that this is potential changes. I want to highlight that the model does not consider impacts of firefighting. It is simulating the changes in fire regime, and it's up to us to value or judge if there is an increase in fire sizes, how we see that as a perceive that as a society, and say, well, this is what we can tolerate or not tolerate. And with that, I would like to thank you for your attention, and yeah, if there are immediate questions, I can answer them.
Thanks, Kirsten.
Yeah, sorry, and I forgot to give credits. You saw the different logos. Of course, this is a contribution of people in Work Packet 3. So Senckenberg, Meteogrid, and also French partners contributed to this work. Thank you.
Okay, thank you, Kirsten, for such a comprehensive and detailed presentation. There's a lot on there, so just a reminder, these presentations will be made available via the website, and we'll send a link out. So if there's anything you missed during the presentation, then we'll be you can get access to it. So we have a little bit of time, and I don't want to start the next presentation early, just in case somebody is planning to join at 10:50 to listen to Angel. So Matthias would like to take this opportunity for 5 minutes or 1 minute, depending on. He has a question for you.
Okay.
Yeah, Kirsten, thank you for your presentation. Yeah, in order to cover, let's say, 5 minutes, I have a follow-up question. You saw that in the chat there was a lively discussion about the wildland-urban interface and fire risk management and biodiversity. You also are working not only on fires, but on biodiversity. How do you think can we include, let's say, issues of the wildland-urban interface, and how can we save, let's say, biodiversity in your model scenarios? And can you make any estimates how these interactions might, let's say, if you account for them in the model, might affect the changes in future fire risks?
At the moment, we have a rather coarse approach and assumptions on how we simulate human-caused ignitions. We center them around urban areas, but I see with the wildland-urban interface, this is something where the risk will increase, and even in these areas, the dark, maybe if I go back to the map. Oh, okay. Sorry, my computer's slow. We will see where we have these stark increases in burnt area, also that there's the risk of wildland-urban interfaces because of so much fuel that is newly under risk to be burned, that this risk can increase. For biodiversity, we are simulating natural vegetation, even though in a simplified way. Adding more biodiversity in our simulations would mean we have considered a larger response diversity. So it could be that the fire risk is there from the climate situation, but for the burnt area, it might be even go lower because we have even a better representation of the natural dynamics, so the microclimate in a diverse forest, and compared to a pine monoculture, could even reduce the potential natural area that could burn. So I think there are possibly risk in two ways. One hand, with more biodiversity, I see the chance of reducing the fire risk and also the vulnerability of the ecosystems. And on the other hand, with increasing wildland-urban interfaces, we are increasing the perimeter, the interface of having more human-caused ignitions. And with the risk that fires can become more extreme. We risk that single events, something that we did not capture in these, say, average simulations, they can still become more extreme. So this is something we should really have an eye on. And it also means we have this in our hands. So talk to the people, explain them the situation, raising awareness for being really careful when there's a drought spell and it hasn't rained substantially in months, that there's a huge fire risk, and yeah, try to avoid threatening the vegetation.
Okay, thank you, Kirsten, for this explanation or your view on this interface between wildland-urban interface, biodiversity. Maybe a short follow-up question. What do you think is the higher risk at the wildland-urban interface? People causing fires in forests, or the forest fires burning into the villages? What do you think is the biggest issue?
I must admit, I haven't worked in detail with the wildland-urban interface. Maybe this is a question we should save for the afternoon, for when you have the specialist from the University of Haifa. I would say it's the people, because they are setting the fires. And so if they are careful when they're wandering around in the area, they have control of what might be going on, would be my say in it.
Okay, thank you, Kirsten.
Okay, thank you very much, Kirsten. And next up is Angel Carrillo from GMV in Spain. Angel will be talking about forest condition and biotic damages, specifically in this case, the bark beetle, which was mentioned in one or two earlier presentations. So Angel, over to you. Thanks for coming.
Thanks, Chris. I'm going to share my screen. Okay. Can you see the screen?
Yes, we can see the screen. It's just in the non-expanded
Perfect.
view. So yeah, perfect. All yours.
Okay, thanks. Well, I'm going to present our bark beetle attack predictive model for this pilot site of Central Europe. So let's start. This is a general workflow of our methodology, which is actually quite complex, and here is very simplified. By basically we use Sentinel-2 composites to derive a spruce mask and a bark beetle damage estimate classification, and then we use that bark beetle damage estimate to train different machine learning models using environmental traits as predictive variables. So our objective was to be able to predict the areas with higher probability of suffering bark beetle damage before the start of the bark beetle season. And well, with that we produce a bark beetle predictive map, and then we validate it. Okay, so as I said, our first step was to obtain a spruce classification. We use Sentinel-2 composites and National Forest Inventory data sets, and also current land cover to train a random forest. And well, we obtained this spruce, non-spruce classification. You can see these are the performance metrics of the validation process. So we validated it with 20% of the training data set, which wasn't used for training. And well, you can see that the overall accuracy was quite high, 91%. Also the F1 score was 86%, so quite decent. And then we used this spruce classification map to derive our bark beetle damage estimate. For this, we used an algorithm that we developed several years ago and was published in remote sensing. The main objective of the algorithm is to detect the occurrence of barbital and to map the area affected by the damage. And basically it uses 3 indices, which are the NDVI, the leaf area index, and the normalized difference moisture index, to obtain a baseline of vegetation health. And then we adjust a multi-temporal simple linear regression to images, Sentinel-2 images before and after the barbital attack. And we use the regression errors to estimate the area of damage. And this is how it looks like. And well, here we start to see the first problem. So we didn't found any standardized data set of barbital damage encompassing all the pilot site. But thanks to Chris and the Technical University of Dresden, they provided the barbital data records. So we were able to validate this only in the Saxon-Switzerland National Park. So it's not the best because it's a small area within all the greater pilot site, but well, the results were still quite good with accuracy and F1 score both above 80% and relatively low errors. Of course, it's highly desirable to have a greater area to validate, but for the moment we didn't get any better data set. So this is what we have. And well, now we come with the interesting part, which is the predictive modeling. Well, we reviewed a lot of literature to try to establish which factors predispose forests to barbital attack. And after the review, we were able to, let's say, derive all these variables that are in the table using different sources. So the spruce density and stand density were obtained from Sentinel-2 data with the same methods as the barbital damage estimate and spruce mask. The natural spruce distribution was provided by the 4Gen. The habitat pressure and protected areas were provided by the European Environmental Agency. Then we used the digital elevation model from Copernicus to derive different topographic features and also the solar irradiation. The soil type was provided by the European Soil Database. We estimated the draw in previous seasons using data from the European Draw Observatory. And well, we used climate data, temperature, precipitation, and wind speed from ERA5. And we derived different barbital attack density and distance indicators based on our methodology of the barbital damage estimate. Well, you can imagine all these factors were in very different formats and resolutions. So we need to apply a quite complex process of cleaning and normalizing all data sets. But this is just to highlight some of the special transformations that we apply to some kinds of data. For example, the aspect we transformed the original degrees to the sin and cosine to be able to be ingested by the model. Well, we performed different kernel analysis for the barbital density. The precipitation and temperature were grouped according to different recommendations of different papers. And well, the categorical features were transformed using the one-hot encoding and multiple correspondence analysis. That, for those of you who don't know what this is, it's like PCA, like principal component analysis, but for categorical variables. So basically, in the machine learning world, it is used as a dimensionality reduction tool. And well, after all these variables were normalized and at the same resolution, we computed the Pearson correlation coefficient of all variables to try to reduce our data set and mitigate collinearity problems. These are the pairwise Pearson correlation coefficients. The main correlations were found for climate data, which is quite logical. Temperature and precipitation are quite correlated. Also, elevation showed a high correlation with climate factors, and well, the barbital density and distance features were all somewhat correlated. And well, finally, these were the selected factors. So we discarded all those variables with correlation coefficient higher than 0.95. So basically, we discarded some of the precipitation and temperature features. We actually only duplicated data, but for the rest, we left the original data. Okay, then we with all these variables, we compare different machine learning architectures. So it's important to say that it's not in the slide that our target was the estimation product that we had developed. So we used our barbital damage estimate, and what we did is to try to model this damage estimate with all these factors from the previous season. Let's say to see if we could predict more or less the areas with higher risk of suffering barbital damage. So we compare, these are all regression models. We compare the linear regression, random forest regression, support vector regression, XGBoost, and LightGBM. Each one of these has its own advantages and disadvantages. We adjusted the hyperparameters through grid and random search, and we found the random forest regression to be the best model. So the R-square was not very high, actually. It was 0.54 in training test. It's basically the same. But the root mean square error and mean absolute error are low, so it's still a good result. We can discuss later why this. And well, the first output of our random forest model was the feature importance ranking. So just to summarize, we can say that features related with forest structure, which are very few, only spruce density and stand density, explain 35% of the variance of our model. In second place, the previous attacks, so the density of barbital damage in previous seasons and the distance to the areas attacked in the previous year accounted for 25% of the importances. Topography yielded a similar result. The climate variables only explain 10% of our model. We expected a bit higher value, but it's important to consider that the ERA 5 data set, so the resolution of the data is between 1 and 10 kilometers, so it's likely that with higher resolution data provided by meteorological station or whatever, the results could be, so the importance of climate factors could be higher. And well, then finally the categorical variables only had a 5% of importance. And it's very, very important to bear in mind that we are missing some of course, some variables, but one of them is the forest age, which is very important. It's pointed out by all the papers that we have found as one of the main variables triggering barbital attack. We couldn't find any data set which was adequate for our approach, but so if forest age was included, this result would have been somewhat different, I think. So this is the result. This is how it looks like, the barbital predicted attack. So as you see, it's a map ranging from 0 to 100. 0 means that there's no predicted barbital attack, and 100 is that 100% of the pixel is predicted to be basically full of dead trees by barbital. Here you can see a comparison between the predictions and the estimates. You can see that the areas more or less overlap, so it's apparently a good visual result, at least visually. And well, with the validation, we had the same problem as before. We could only validate it for the Saxon-Switzerland National Park, and as so our reference data was binary, was damage and no damage, and the output of our model was a continuous variable. What we did is to binarize this scale according to different percentages. We started with 50%, so considering that above 50% it was damaged by barbital, and below 50% no damage. We optimized the F1 score because it was the metric that was it's most suited for this kind of tasks. And well, we found that 35% was the best threshold. The accuracy and the F1 score were very high. Also, commission and omission errors were low. The bias also low. So it's only for the Saxon-Switzerland National Park, so it's not very a really good validation, but it's what we had. Well, just to conclude, we can say that barbital attack can be predicted to some point using freely available data. Also, we implemented that semi-automatic pipeline, so it's easily replicable to other areas. We obtained very good performance metrics in general with the limitation of the validation datasets. The errors were low, and the feature importance, well, we built some interesting outbreak predisposing factors. And just to finish, I would like to highlight some of the important limitations of our work. The first one is some environmental traits were not included and should be included. The forest age is one of the most important, and we need to include this to make the model more robust and reliable. Then the lack of validation data, as I said before, we had many different countries, many different methodologies for national inventories, and it was very, very, very difficult to find a strategy to validate our product. And then the low resolution of some data sets as climate. We were a bit forced by time, but with a bit more time, we could have been able to derive higher resolution data from climate stations or meteorological station or whatever. And well, thanks for your attention. I think I'm more or less on time.
Yeah, thank you, Angel. I mean, the debate will rage on about the spruce, and I suppose in the future we might be looking out for other biotic damages and diseases that might get worse as the climate changes. So now I'd like to invite Angel's boss, Maria Julia, to present a survey about some of the products and tools and information that you've heard and seen today, and about what's important to you as various stakeholders and the various parts that you occupy in terms of forestry, whether you're a forester or a town planner, a regional planner, a scientist, and we'd like to hear from you. So Maria, it's over to you to introduce yourself and to introduce your slot. Okay, thank you very much.
Thank you. Thank you to you, Chris, and congratulations for all the organization. Can you see my screen?
Yes, we can, yeah.
Okay, thank you. So now here we come close to lunchtime. So before we go into the break, okay, I will not issue more information. So this is more like a break-up time. Just give me in the range of 10 minutes. And also, if we have some extra time, some questions could pop in. But now, I don't know if you have been following the attendance, but we have been present in the range of 80 to 90 people, although some people have been coming and going. At the moment, we are in the range of 75, 78. So what we would really appreciate, and just to summarize and to go to lunch with a good summary in our minds, is to pass a couple, some 3-4 questions. This will be good fun and quick. So I kindly ask all the audience to have at hand their mobile phones, their smartphones, because I wanted to carry out a questionnaire online. You will see the results on the screen, time live in real time. So then for this, we are going to use this application, which is very friendly, which is Menti. So I kindly ask you to type in your navigators this www.menti.com or scan the QR code so that we go into this common activity. So please, I'll give you a minute for it. Okay. So then what we would like is to, first of all, to give you an overview of who has been here this morning, because since we are online, perhaps not all of you have a full picture of who you have been with. So we would like to know your organization's name, and please, I would like to say as well that this questionnaire does not hold any personal data, so you can feel at ease on that. So then here you see the institutions that we've been listening to this amount of information of valuable analysis and products to prevent and attack wildfires throughout Europe, and focusing on this Central European area. So just 21 responses. I think that we are more than that. We'll wait for a minute. So okay, no more answers here at the moment. Not sure, perhaps some attendants couldn't get the Menti link number. That might be the case.
Matthias has just re-added the link in the chat for anybody who missed it. Okay.
Thank you. Perhaps I was too quick at the beginning. Okay, so then for the moment, let's leave it at that, and then we move. Something went wrong. Trying to show this slide. Mhm. Sorry, not sure why this is not working.
Julia, just click on the
Yes.
reload.
Reload. Okay.
And I have my fingers crossed.
Hold on a second.
There we go.
Here we go. Good. So we would like to know what component of the wildfire risk is most important in your activity. So here we give you some ideas, but in the next one, if you don't see your risks represented, you will have a chance also to express it. You can vote or point at maximum three causes, and then submit it. Perhaps all of them are important or present, but we would like just to focus on the three most important ones. So fire propagation, fuels, and terrain are is the most voted, followed by human and natural ignition causes. Okay, let's wait just a little more. Okay, it seems that no more answers are coming in, so let's move ahead. So if you didn't have enough time to grab your mobile at the beginning, you can join any moment. Just type www.menti and the use code number that you see at the top of the slide. So let's continue. Next, what other wildfire risk components do you deal with in your activity? So this is free. Just tell us shortly keywords, perhaps, but that illustrates perhaps some other areas or aspects that we didn't account for before. Okay, wildland urban interface, we will see that this afternoon as well, but it's good that you pointed out risk assessment. Okay. So forest management and fuel management suppression tactics, procedures, fuel flammability, burnt areas, again, while an urban interface, yeah, that's a real issue. Fuel management and yeah, I would say forest management. So all these ideas are great for us also to evaluate which of these products could be most useful where. So thank you. Fuel vertical structure. Okay. Okay, not to keep you away from lunch, let's move ahead. You have seen this schema a good number of times. Just a flashback to remember what we are looking at to this fire danger, fire exposure, and vulnerabilities. So we are going to go now directly to the products that we have been presenting this morning on fire risk assessment, reduction, and adaptation. Okay, so all right. So for each one of these products for which you have received these details, we would like to know if the explanation has been sufficient. Again, if it hasn't been, don't worry. You will have the opportunity to say what else you were expecting. Okay, in your mobile phones, it's quite easy to value each one of the products that you have been attending to. So here we have the first results. And now they are getting more balanced. So clearly the human ignition probability and the wildfire spread are important. Also the biotic damages, which in this area are manifest. Okay, so far we have 16 people voting, 17. Okay. So thank you, because with this, after we will be able to also show some graphical summaries. I continue, and now we would like you to value how suitable these fire risk products, fire risk prevention products are for your territory. So in the same format that we voted before. Actually, we tried to bring to this demonstration initially the ones that were more, that we found out of some previous questionnaires, the ones that were most suitable for Central Europe environmental conditions, of course, and for the future, and the transboundary situation and topic that we wanted to look at in this session. But then again, this suitability allows us to make better adjustments. Okay, I'll wait a little bit more. Then we are nearly there. Don't despair. I move to the next one. So what other information about fire risk, either assessment, reduction, or adaptation, would you need? In some instances, the availability to thematic databases has been pointed out. climatic series, better resolution in the data sets. Yeah, more standardized and accessible data. So here somebody also pointed out at products in themselves, like the firefighting index, post-fire natural vegetation recovery and change, prescribed burning guidelines. That's very different across Europe. Yeah, finer resolutions of the data. Yeah, the spatial resolution is always an issue. Okay. So as no more ideas are coming in, I move. And I think this is our second last. We would like to know how comprehensive the approach, the scientific and the usability, the applicability of the products has been for the application. So please let us know if the explanation has been sufficiently comprehensive, or perhaps in some of the products you would need to, I mean, more details on how it has been developed or the results obtained so far. Okay, we will try to examine the causes of the gap between the maximum comprehensiveness and the value that we got for each one of them. Thank you for your responses in this, and let's go to the last one for this moment, because this afternoon we will repeat this exercise briefly. But now we come to the last question here, which in fact we ask you for two things: the usability and the interest that you have for these products, how usable it could be in your protocols, in the normal tasks that you have to accomplish, how usable the products are, and the interest. Perhaps you are more on the side of the first responders, and some of them are more theoretical, so the interest is lower, but you see the usability. Okay, so we wanted to combine these two factors: usability and interest. So here we have some of the products. So still some responses coming in. So overall, all the products fall in a high usability and high interest. Perhaps I would highlight the wildfire spread, the forest condition and biotic damages, and the future fire regimes will be the winners with this quick view. So there are no more answers coming in. I thank you so much for your responses down to this moment. And yes, please.
Sorry, I just wanted to make, I mean, people have got a little bit of time now during the lunch, if they're not busy eating. Will this survey be open during the whole lunchtime, you know, for the next couple of hours? Will people be able to, maybe there's some people that took quite a long time to type some stuff in, or so maybe, can you leave this on the screen and it'll be open during lunch?
The point is, no, it's not possible to answer the questions offline. But however, this afternoon, I will show and we will notify how to access yet another possible questionnaire in which, I mean, it's not so fast, it's not so immediate. And whoever wants to provide us with answers more at peace, you can access it. I will give the link to it so that at peace, with time, it will take you something like in the range of 15 minutes to respond those questions, and then you can also provide us with your feedback.
Okay, thank you, Julia. I'll give a link after the meeting.
Thank you.
I'll send a follow-up email to all the attendees.
Okay.
And you'll get a link to the presentations, and we'll provide a link for the additional online questionnaire as well.
Okay, but nonetheless, if I can say, I advance that this afternoon, after the presentation of the next products, we will have a similar session like this one for part 2. So please have your mobile phones at hand.
Okay. Okay, many thanks, Julia.
Thank you.
Okay, so I'm going to declare a lunch break 4 minutes earlier than planned, which is unheard of normally for these types of meetings. And we will see you back here, same address, same link at 1:30.
Thank you.
Okay, thank you very much, Julia. Okay, bye-bye.
Bye.
So, 1:30, welcome back. We got refreshed, had some lunch, and we'll start with the third session today. And this is Valerio, you have to excuse my pronunciation name, Valerio Pampanoni.
Great.
From the University of Rome. And he's going to switch around his presentation. So it's slightly different order from the agenda. And he's going to start with satellite-derived live fuel moisture. Valerio, the floor is yours. Thank you very much.
Thank you, Christopher. As Christopher anticipated, we'll be presenting live fuel moisture content product before, but live fuel moisture content product is involved in the daily fire danger index we'll be seeing later. And also, I should clarify that while this live fuel moisture content product is indeed part of the products that will be that were developed within Fire Risk and will be shared using our internal platform, the second presentation is something that was basically a secondary output of this product. So this is an official Fire Risk product, while the other one isn't. But of course, what is live fuel moisture content? Many of you will be familiar with it. It is defined as the weight ratio between leaf water content and dry matter, and can be calculated with a simple division. In the conceptual Fire Risk integration scheme, which you've probably seen multiple times by now, we're dealing with fuels, we're dealing with ignition and propagation. Why are we interested in estimating or measuring live fuel moisture content? First of all, live fuel moisture content has an important role in determining the nature of the interaction of fire with live fuels. For instance, different levels of life field moisture content will determine whether or how easily a fire will start, the severity of that fire when it started, and how fast will a fire spread. And you can imagine the significant interest in measuring or at least estimating life field moisture content. Regarding measuring life field moisture content, usually it can be done using gravimetric techniques, which basically involves going into the field, gathering samples, weighing the samples before and after drying them in special ovens, so that we can eliminate the water part, the water component of the that was contained in the leaves, and then calculate the ratio between the water that was there and the actual dry matter of the leaf. But as you can imagine, this process is long, it requires manpower, and it needs to be conducted multiple times throughout the year, often even on a weekly basis in some parts of Europe, and requires knowledge, know-how, and equipment. So it's a costly and time-consuming effort. So how do we estimate it? Even if we work with satellite data, so we have basically all the possible information at our disposal, because we will not be limited on a spatial scale, so we'll be able to access data from all over the world without limitations. In this case, machine learning is not the solution if we want to develop a European or a global product. In this slide, you can see the distribution of the most important life field moisture content field datasets, which we could use potentially to train a life field moisture content product based on satellite data. But as you can see, the vast majority of the datasets are divided between the United States, in particular the Western United States, Western Mediterranean Europe, and Australia. So yes, in theory, we could use machine learning, but we would be severely limited in the applicability of this product, at least, using just machine learning. So that's why we still have to rely on a physical basis for our life field moisture content product, which is provided by the combination of two radiative transfer models. One, which is Prospect, which is basically a model that let us represent the leaf on a biophysical basis, which is actually what allows us to link the leaf with its water content and dry matter content, and then get back to the life field moisture content. Sail, which allows us to get the leaf and spread it over a canopy, and basically to model the canopy, and also to model the observation geometry in terms of the position of the sun and the position of the observer, which in our case is a satellite. The theoretical basis of this work relies on the only existing work that was done on developing a global field moisture content product, which was done in 2021 for the NASA satellite MODIS, and is still currently the only existing satellite life field moisture content product which has been published. And our model is very similar. The theoretical basis is the same. We use the combinations of these models to model 3 different vegetation species, which are grass, shrub, and trees. And basically, we use the models to represent different types of vegetation and different conditions of the vegetations, so that hopefully we are able to recognize the life field moisture content values without having any further information in terms of field datasets. And that is what allows us to have potentially a European product or a global product, which we would not have if we only relied on field datasets, which, as we saw, are not homogeneously distributed. In our case, apart from the modelistic side, which involves the radiative transfer model, we also used some machine learning, actually, but only in the inversion part, which means that we're using it only after we have run the physical model to get back to the regional variables, which are basically what we care about and what gives us the life field moisture content estimate. Basically, once we have run the model forward with all of its input variables, which describe the leaf, which can describe the architecture of the canopy and many other things, what we obtain is a radiation spectrum, a reflectance spectrum. And what we are able to do is basically to simulate the observations that we will get from a certain satellite platform. What we have to do, of course, is the opposite. We will get the satellite observations from some satellite, and we want to estimate the life fuel moisture content. What machine learning allowed us to do is to make this operation of getting back to the original variable we care about much faster, and is actually what allowed us to shift the scope of the product, which originally was only confined to the pilot sites of the FireEase project, to the entire European territory. Our main challenge at this point is actually to get around the clouds, basically, because since we're relying on optical satellites, of satellites which observe, in the visible spectrum, we will be, limited somewhat by clouds, and that is especially a problem in Central and Northern Europe. So what we do is basically provide a daily product at European level with the best observations in the last 10 days. The satellites we rely on, in particular for the European level, are 2 European satellites. In this case, we've got Sentinel-3, which is a platform involving 2 satellites, Sentinel-3A and Sentinel-3B, which provide us with a very good revisit time, which is actually shorter than 2 days, which basically gives us a new observation of a certain area every less than 2 days, basically, which is even too much, maybe, for a life fuel moisture content in theory, but is what helps us to, solve basically most of the time the cloud problem, because having so many observations means that if one day we get a cloud, we may not get the same cloud in the same place one day later. So we always have fresh observations. And the resolution of Sentinel-3 is 300 by 300 meters, which is, optimal for a European scale product. In addition, we're also testing a high-resolution product, which is based on Sentinel-2, which here I wrote 10 by 10 meters resolution. It's actually 10 to 20 meters, depending on the band, but the product we're producing at the moment is 10-meter resolution, which allows us, to target the smaller scale, the local scale, or even the wild and urban interface with a longer revisit time. So that is the disadvantage of Sentinel-2. Since we have a 5 days combined revisit time from the 2 satellites. So in this case, if we have clouds, it can be more of a problem because we'll have to wait more days to get new observations. This example you see here is actually one of the last product we generated at the European level. You can see, many holes here. This map of life fuel moisture content is from the 20th of January. You can see the many missing spots, which are basically days for which we have had continuous cloud cover in that area, and we weren't able to get enough observations to provide a reliable estimate. But in general, we can see how life fuel moisture content tends to be very high in the northern parts of Europe, and we still have moderately low or average life fuel moisture content in, for instance, in central Italy and in eastern Spain. This is what you get usually in the summer, where clouds are much less of a problem. And this specific product you see here is from the 25th of July. Here we've basically got the entirety of Europe covered. We can see how, compared to the previous map, the life fuel moisture content levels are generally lower, in particular in southwestern Spain and southern Italy and Greece, while the situation gets better and better the northern we go. At this point, I thought I would show you some example, from the Bohemian Switzerland National Park wildfire. And to do so, I will show you both products, actually, starting from the moderate resolution one based on Sentinel-2. So this is what we had at the pilot site scale. So this is the Central European pilot site. This is the life fuel moisture content we got on the day, basically, where the Bohemian Switzerland wildfire started. This lower life fuel moisture content patches here are mostly agricultural fields, so they're not usually a problem for wildfires. but the situation changes when the Bohemian Switzerland fire started. I don't know if you can see it from your screen. I hope so. So I will circle it. There it goes. These small fires here represent the satellite detections from the NASA VIR satellite of the Bohemian Switzerland wildfire. So let's zoom in and see what the life and moisture content looks like. Here we are at the border between Germany and Czech Republic, just close to Bad Schandau. And these are the very first detections we got from the satellite, which started between the 24th of July and the 25th. This cluster is basically all contains all the detections that were recorded by the NASA VIR satellite between the 24th and the 29th of July 2022. And this is what the live field moisture content looked like from Sentinel-3 on the 25th. So I saw this patch. I thought I would start on the 25th. And the first thing I saw was this patch of very low live field moisture content, which is rather unusual in a forest. So I thought that probably the satellite overpass happened after the first fires started and then got back to one day. This is the live field moisture content from Sentinel-3 on the 24th. And you can still see how this patch here, where the very first detections happened, was suspiciously dry. And in the following days, the wildfires would spread mostly to the east of the first patch. And as you can notice, they tend to spread more easily to the east. You know, of course, there are other conditions that contribute to where the wildfire would spread. But we can see that the areas that burned were actually areas with lower field moisture on the eastern side, where on the northwestern side, we generally had higher live field moisture content and less fires. But at this point, I would also like to show you what the high resolution live field moisture content product looks like. Now, in this case, this image you're seeing has been generated by overlaying two different satellite images, one acquired on the 22nd of July and the other on the 24th. Actually, on the right side, you can see this, you know, this diagonal line where the two images are joined together. And here you can see all the detections from the 24th to the 29th. You can already probably notice how the level of detail has increased because we went from 300-meter resolution to 1020 meters. Zooming in, this is the area of the very first detections. So it's the area of the detections that VIRS acquired on the 24th of July, sorry. And the images you're seeing is a Sentinel-2B image acquired on the 22nd, so 2 days before the earliest detections. And you can see how the first fires that we're seeing were actually in correspondence of very dry patches of trees. For reference, this is what in the same exact area Sentinel-3 looks like. So Sentinel-2 gives us a much higher level of detail at the local scale, which allows us to make more interesting, you know, assumptions about what happened and about the state of the vegetation. Zooming out again, this is what the entire cluster of fires looks like at the Sentinel-2 scale. Again, the level of detail is much better. So it makes sense, you know, sometimes to use higher resolution products, you know, for localized, smaller scale analysis. And this is what Sentinel-3 looks like at the same exact, you know, spatial scale, the same exact scope. The product validation is still ongoing. We actually published a conference paper with the help of our colleagues from Portugal, ADAI, and our colleagues from Sardinia of the CNR, where we attempted an early validation of this product using field data provided by both ADAI and CNR. I won't go into detail here, but ADAI was tracking 4 species in their field site, and we got good correspondence with 3 out of those 4 species, 2 tree species and 2 shrub species. In Sardinia, we had a slightly, significantly actually larger field site of very homogeneous. And the correspondence was very good with the average light field moisture content of all the species, and still good with a single species, which was a juniper species. But validation, as I said, is still ongoing. The next steps we'll go through, what we want to do is basically to complete the validation of both products at a global scale, also by incorporating new data, but new field data, which was acquired by the Dresden University in the Tharant area and close to Dresden, and also data provided to us by by Florent, by our colleague from the IRD. And we also plan to include external datasets such as global FMC. The results will be published in a journal paper, and the dataset, specifically the European level dataset, will be publicly available through the FireRisk platform, and hopefully also through the FireRisk viewer. This is my contact if you want to send me an email later, but it will also be available for Q&A. But I will actually now switch to the second presentation, and I think I have to stop sharing and share a different, forgive me, but I have to share a different presentation. There it is. Oops, no. Wrong presentation again, sorry. There it is.
No panic, you got plenty of time, Valerio.
Yeah. Just, they look exactly the same, so I got confused. There it is. Again, I will remark that this is not an official product, but this is actually a secondary output of what we saw before. And I will go and I will explain why it is in a few seconds. Now, the terminology is usually complicated when it comes to, wildfire science, because we usually got different definitions of fire danger, risk, etc. So first of all, I will clarify that by fire danger, we refer to the likelihood of fire ignition and propagation. So this is what we mean when we talk about fire danger in this case. And again, we're basically dealing with the fuel status and the weather conditions. So basically, we need, in order to have high fire danger, we need to have both high ignition and high propagation probability. So if we have high fire danger, the fire will be not only more likely to ignite, but also more likely to propagate. While if we have low fire danger, even if we purposely ignite a fire, that fire will be less likely to propagate. So what we're dealing with is basically the state of the vegetation. So why develop a new fire danger index, since there are so many, existing ones and also so many established ones which have been proven to work rather well? Well, first of all, the European Forest Fire Information System has been using for many years a custom version of the Canadian Fire Weather Index as its main fire danger index. And the Canadian Fire Weather Index is a very good index. It is convenient in the sense that it uses only weather data, but using only weather data most of the times limits it on this spatial resolution side. Of course, it is a reliable time-tested product, but its level of detail is sometimes sufficient when we want to get to the smaller spatial scales. For instance, the latest product that has been distributed by the ECMWF, on behalf of EFIS, has a resolution of 0.1 by 0.1 degrees, which is basically 11 by 11 kilometers, which is, rather coarse. So to this end, satellite-based fire danger indices offer a series of advantages, such as global applicability. They also can incorporate weather data together with the satellite data, but most of all, they allow us to get so let me get the pointer, high spatial resolutions and a high update frequency. One of the very first fire danger indices developed for satellites dates back to 1994, and our fire danger index is basically in that tradition, and I will explain why in a few moments. Again, we're targeting the same satellites I talked about before. So Sentinel-3 for the for the larger spatial scale in Europe, and Sentinel-2 for the smaller spatial scale and the Wilder-Unbar interface, for instance. And again, as a fire danger index, we are targeting a series of variables which can be divided into static and dynamic. But as a satellite-based index, what we're more interested in is being able to get new and updated observations of the fuel status, of the vegetation status on a timely basis. So what we do is to incorporate the light fuel moisture content estimates we have seen before, together with vegetation greenness estimates we can get from satellite images, into a new product which will be at the same resolution of the satellite images. And this is actually where the fire danger index, based on satellites I was mentioning before, started. So when NASA developed the fire potential index, which was based on the ability to estimate vegetation greenness using long-term satellite observations. And at that point, in the same book where NASA proposed this fire potential index, they said they were not ready to get light fuel moisture content estimates from the satellite, but they were already capable to do so for vegetation greenness estimates. What we can do today is actually incorporate light fuel moisture content estimates from satellites, so we can actually continue on that tradition and develop a novel fire danger index based on satellites. So the light fuel moisture content, we've seen it before, is the same exact product you have seen. And we also include other variables of fire danger, which can be calculated using ancillary data and weather data. One of them is the dead fuel moisture, which is also very important in determining fire danger, and is thankfully much easier to estimate than the live counterpart moisture content, because dead fuels basically respond to the weather conditions, so they can be modeled pretty accurately. We also take into account the evapotranspiration, which is used basically as a measure of hydric stress of the vegetation, and also it's what allows us to incorporate the effect of the topography and the effect of the actual hours of sunlight that reach the surface into vegetation stress. So the idea is that high evapotranspiration will be associated to more stressed vegetation and to higher fire danger. And finally, wind speed, which is also quite complicated to include in satellite-based fire danger indices, because there are many different opinions on whether to include it or not, because of course wind speed can change unpredictably, and the scale is also very important. But we also include a simple wind speed variable as our fire danger variable. And the model of the daily fire danger index is a simple additive model, including all these variables. And what we thought is to calibrate this additive model with coefficients whose values would be assigned depending on the historical recorded wildfire history of a given target area. And to do so, we basically used a random forest model fitted on the historical wildfire records, specifically in terms of fire radiative power, onto different pilot sites and demonstration areas. Now, the problem with Northern Europe, which Matthias also talked about earlier, is that there is less data for calibration because we have fewer fires and also smaller fires compared to Mediterranean Europe, for instance. And unsurprisingly, that resulted in wildly different results in terms of coefficients, which would highlight the importance of a given fire weather variable compared to the other for that specific region. For instance, in the entire PS2 side, so in the entire Central European side, we basically got very high importance for light fuel moisture content and for evapotranspiration, and very low for wind speed, while the others were almost comparable with Sardinia and Central Portugal. So mind that these results should still be validated and need more data. So again, I used the Bohemian Switzerland fire as a case study. So these are the same slides I showed you earlier with the first detections and the entire wildfire detections from VIIRS. from the 24th to the 29th of July. And for reference, this is what the fire weather index used by EFIS shows on the 24th of July, so the day the wildfire started in Bohemian, Switzerland, at its native resolution. I don't know if you can tell, but we are basically at the border between a few pixels. I think in the entire image we can count 6 pixels, because the resolution of this product is 0.1 by 0.1 degrees. Now, if we switch to the prototype fire danger index we are attempting to validate, this is what we have, what we get in terms of resolution. In this case, we are looking at Sentinel-3, so at a 300 by 300 meter resolution. Now, while the product still needs to be properly calibrated, so I'm not very confident on its ability to discriminate danger levels, we can already see how in the area where the wildfire started on the 24th, we have higher fire danger. And again, the fire developed towards the areas at higher fire danger. Now, doing the same, having the same conclusions on a coarse resolution product based only on weather data would be much more complicated. So this is the benefit in having, developing a new fire danger index based on satellite images. We could get potentially much higher resolution products, even at the national scale or at the European scale. But again, this is still, these are still preliminary results. We still need much more data to calibrate and validate the product. What we aim to do is to continue acquiring data and possibly use the same validation procedure we used for Mediterranean Europe. But again, since we'll probably never reach, the same amount of confidence we get with the much more wider, wildfire records in Mediterranean Europe, we may also attempt to develop a different calibration and validation procedure for Northern Europe, which does not require as much data to get high confidence. And again, we also aim to transfer the fire danger product at the local scale using Sentinel-2 to, provide a local scale product and also possibly to target the wild urban interface. And this is it. This is my email if you want to contact me later with more questions, but I will also be available, shortly for Q&A. Thanks.
Okay, great stuff. Thank you, Valerio. Really interesting.
I hope I'm in time.
Yep, great. Valerio will be open for questions and it'll hang around in the Q&A if you need any further details. Okay, next up is Angel Canel from University of Jeddah, and he'll be presenting the work of Victor Roco de Dios, and he's looking at the fire danger metric. So Angel, you can share your screen now. Thank you very much for coming.
Yes. Hello. Sorry for my English. I have a basic level of English and I may not understand some things, but Victor Resco has not been able to be here, and for the reasons he has recorded the PowerPoint explanation, so I just put it on. And apologies again because I won't be able to respond if there are questions at final.
That's okay. What we'll do is we'll record any questions that the audience have and we'll pass them on to Victor afterwards. Okay?
Okay. Mm-hmm.
Okay, Angel, we've got a slight problem with the sound at your end.
The sound, no?
No, we can't hear, Angel.
Vale.
we have developed this new metric. Hello, good morning. My name is Victor Resco de Dios, and I work at the University of...
Okay, we can hear it now. It's quite quiet, so I suggest the attendees, if you just turn up your volume, you should be able to pick this up.
In relationship to some work to...
So,
Yeah, Christine says it's fine. Okay, try once more, Angel. The last time you did it, you had some sound and it was a little bit quiet, but I think the attendees can turn up the speakers on their computers and we should be able to hear it.
and how to solve it?
Okay, just start the recording again, please.
Yeah.
Hi, Christina.
Hello. Ángel, do
¿Qué?
you need some help, maybe?
Dime,
¿Necesitas ayuda para que empiece el vídeo?
¿cómo se tiene que hacer?
Mira, tienes que darle al icono del centro de abajo que te pone compartir pantalla.
Sí, eso está hecho.
Y luego darle en el PowerPoint a la flecha de que comience.
Sí, está hecho, pero no suena.
¿No suena?
No.
¿Lo intento yo?
Sí.
Vale, pues comparto yo pantalla.
Vale,
Tienes que dejar de compartir tú.
de acuerdo, voy.
Oh, we are going to try from my computer. Sorry.
Okay, no, there's no need to apologise. These things always happen. I'm glad it hasn't happened to me this morning, so. All right, thanks for your efforts, Angel. Let's see if we can get this running.
Sorry.
No, don't apologise. It's fine.
Ángel, tienes que dejar de compartir.
Voy. En principio ya está. Ah, vale. En principio ya está.
No, me pone que estás compartiendo.
Salgo, si no.
Sal, bueno, sal, vale. I'm sorry, I get a message that I cannot share my screen while another person is doing it.
Okay, so I'm not sharing my screen anymore, and Angel, you were the last person to share your screen. Let's just check on the panelists. Okay. Asked to start a video. Stop audio share. Can you see anything there, Matthias? Nobody else is sharing.
I think Christina should be able to share.
Okay, apparently you can share. Just try again, please. Try again, please, Christina.
I cannot share my screen.
Okay, all right. That's all. I'm going to share my screen, which will stop everybody else sharing theirs. Then I'll stop, and then let's go.
Try again.
Okay, right. Go share. Okay, fine. I'm going to stop sharing
Okay.
in a second. Stop share. So nobody should be sharing now, and you should be good to go.
Okay.
All right, smashing, brilliant. Okay, thank you very much.
And now I will try to make this work. Do you hear?
Not
Yes.
much. We can't hear anything at this end, Christina.
You cannot hear.
No, I can see Victor and we can see the presentation, but he's very, very, very quiet.
I don't know how to fix this. How can we make it? I don't know. Can you increase the volume in the computers or something? Okay.
Earlier we could hear him just, and now we can't hear him at all.
Okay, I will try to start again.
Okay, thank you.
I will share.
These things are sent to testers. It's
Here.
Current fire danger prediction.
okay. We can hear him just. So I will please ask the attendees if you could turn your speakers up, and hopefully we can.
Understanding fire weather and fire density.
Can you hear if I increase this? Okay, like this.
History. Different countries have developed.
Is it better?
Approaches, and perhaps
Not really. I mean, we can hear him, but it's so quiet.
Well, I have no idea how it was recorded, but I'm certain. What can I do? Maybe can I talk at the same time he's doing it and maybe explain what he's saying? I don't know.
Yeah. Do you know what? Let's try that, Christina. You know, it's
share sound.
share sound
When share screen, there should be a share
on share screen. Christina,
Yes, on sharing a screen.
advanced sharing options, and maybe share sound.
Oh, okay.
Okay, maybe that'll help.
Now
Okay.
that should help. True.
Okay, let's give that a go.
Okay.
Hello, good morning. My name is Víctor Resco de Dios, and I work at the University of Lleida.
It's better, but still a bit quiet.
Víctor Resco de Dios, and I work at the University of Lleida. Today I'm going to tell you, to explain you the work that we have done within the context.
That's very quiet.
It's very quiet.
Work to try to improve current fire danger prediction.
I can hear
we have
fine through my speakers, but I don't know what to do.
As well as atmospheric.
Do either.
So the topic of understanding fire weather and fire.
What do we do, Chris?
Hang on.
History. Different countries have developed different approaches, and perhaps the one that's
Maybe I can comment on what he's saying. He's speaking a little bit fast, but
Sorry. Okay, one last chance, Christina. In the share sound, there are two boxes. One is share sound, and one is it says optimize for video. In the advanced.
Okay.
Okay,
I
let's
check
try
both.
that.
Should I check both? Share
Yeah.
sound and okay.
Do that. This is our last chance. This is our Hail Mary, and then after that, you'll have to give a little bit of a talk over.
So the topic of understanding fire weather and fire densities is not new. It has a very long history. Different countries have.
Okay, we'll go with that, Christina. That will have to do. Okay, thank you.
At least in Europe, is the Fire Weather Index, the FWI, which was developed over 50 years ago by Van Wagner, a Canadian scientist. And it is a very good index. It has a good physical basis, and it relates fire line intensity with the value of the FWI.
Houston, we have a problem.
So as we can see here in these slides, we see the different values of fire line intensity. They correlate with values of fire weather index. One of the problems, however, that we see with this fire weather index is that it saturates very quickly. In that it's going to predict fires beyond extinction capacity very soon. A fire beyond extinction capacity means that fire line intensity is above 10,000 kilowatts per meter. Those of you who are not familiar with this terminology, now imagine one of those small radiators that we can have in the bathroom or whatever, that they have that cylinder that sort of becomes orange when it's heated, and that it emits radiation for heating. So this radiator will emit 2,000 watts. So it's going to be a 2 kilowatts radiator. Now imagine you have 5,000 of those radiators within a meter of the fire front, a linear meter of the fire front. So when that happens, you cannot put out the fire. They're beyond extinction capacity. You can throw as much water as you want, but you're just going to tickle the fire. You're not going to put it out. So with FWI, this happens at values above 39. So if we look at what happens in Southern Europe, we get 39, maybe in April or May. So it saturates very quickly. Another issue that it has is that it is very much affected by regional variability. So we get different values of fair weather index for a given fire intensity. And here in this study that I'm showing here from some colleagues of Portugal, fire intensity is not shown in the upper graph. What's shown is area, fire size, area burned by the fire, which is somewhat an indicator of fire intensity. It's not the best indicator of fire intensity, but it is certainly related in some instances. And it shows that there is a lot of regional variability within FWI. So in order to solve these issues, and especially the issue of FWI saturating very quickly, yielding extreme fires very quickly, what some people have done is to use quantiles, to use percentiles, because FWI can go up to 70 something, 80, 90, it can go beyond that. And what people have done, and this is very common, for example, in the JRC, in the European Forest Fire Information System, that we all can go online and check, FWI is given as a percentile. And if I am not mistaken, the very extreme fires are considered as values above 70. I'm talking from memory, I might be wrong there, but something around that neighborhood. So this is an example of what happened in Pedro Gao Grande, which is one of the most unfortunate and infamous fires we've had in recent years. It burned in June 2017 in Portugal. And in the stations nearby, the FWI values, they were above the 39 threshold, but they were not considered extreme according to this statistical classification. So we did a different analysis, and it is that we looked at dead fuel moisture, and we estimated that from a model that we had developed before based upon vapor pressure deficit. And we saw that this shaded line is the values during the 20 years before. And what we saw was that the fuel moisture based upon VPD was unprecedented. It hadn't occurred, it wasn't beyond the historical record. So it was under really very extreme conditions, which is something that FWI had not been able to capture. It was just measuring that, it was high, but not super extreme. So, there were lots of different things that happened at Pedro Gao Grande. Many of you know the behavior of this fire very well, and it had some very bizarre behavior. And of course, that fuel moisture doesn't explain everything, but it does explain at least part, especially a part of what happened there. So this sort of got us on track to think that, we need to define better, to establish a better system for early warning before the onset of these potentially catastrophic conditions. Perhaps CPD is one way to do that, because this way we can know its effect on dead fuel moisture, but then we would also need to understand what's happening with the atmosphere and with atmospheric instability, because this was the other big issue in Pedro Gao Grande, and something that we see in lots of the big fires that we can expect to have in Europe as the 21st century progresses, the role of pyrocumulus. So the first thing that we did before jumping right into the issue of this metric was to do an exercise. Here it wasn't done in the whole European territory. This particular exercise was done only for the EU Med region, and the reason was simple. We needed a lot of data, and that's where we have most of the fires. So what we wanted to do was to identify which are the critical triggers, the critical switches, which is the set of environmental conditions that if you cross those values, you're gonna get large fires or very large fires. So we divided Europe into different, or Mediterranean Europe into different pyro regions, meaning areas with a similar seasonality in the fire. And then we examined the critical thresholds associated with dead fuel moisture, live fuel moisture, wind speed, as well as atmospheric instability defined on the highness index, and so how those differed across fire sizes for different thresholds, 500 hectares, 1,000, 2,500 hectares, and how those differed across pyro regions. And also how fire size increased with the number of thresholds that had been crossed. During this exercise, one of the problems that we saw was that we didn't really have very good estimates of live fuel moisture. We compared lots of remote sensors. So then we decided to develop our own product for live fuel moisture content, because we couldn't find any reliable estimates for Europe. Unfortunately, at the time we did this exercise, there was only data for Mediterranean Europe, so that's what the database is. But we hope that with the data from Chris and others and that which others have collected, we can expand this to cover the whole Central Europe and also to translate this into Sentinel, because the original model was done with MODIS. And just to highlight that this was led by Angel Cuny, who was a master's student at the time. Then we started exploring a bit more the role of vapor pressure deficit. And for example, we saw whether we can or not predict whether we're going to have fire days, depending upon vapor pressure deficit. So we looked at the distribution of vapor pressure deficit in non-fire days, in days without fire. And then we looked at the distribution of vapor pressure deficit on days where we have fire. And we can see that the distribution of fire days and the distribution of non-fire days are above, non-fire days are below, is very different. So we define as a fire day a day where the probability of having a fire is above 0.5, is above 50%, which is this red line which results from model fitting. So we developed a first metric of whether it's going to be a fire day or not, based solely upon VPD, and it had a relatively reasonable accuracy. We quantified these VPD thresholds for the whole European territory, and so we have this. We can predict now whether we're going to have a fire day or not based upon vapor pressure thresholds. And whether it's going to be a fire day or not, of course, this is going to depend upon the ignition. So fire days, what they are telling us is, if we have an ignition, is that going to propagate? Is it going to spread and become a fire? Yes or no? And we're going to give you a probability. If you tell us the VPD, we can tell you the probability of that happening or not. Then we merge this with different climate simulations, with different GCMs and different scenarios, and we saw that in Europe, as a means, we're going to experience like a 1 day longer growing season per year. We then wanted to make sure the VPD was good, that we hadn't jumped too quickly into using vapor pressure deficit as an indicator of dead fuel moisture. So we analyzed the bonfire database, which had been compiled by our colleague Paulo Fernandez from Portugal. And this is a global data set which incorporates the results from all the experimental fires that are available in the literature. So this is a global data set with lots of data points, and we compared lots of different models. And what we saw was that overall, models based upon vapor pressure deficit, they provided better predictions with less biased predictions and with smaller errors than the other models that have been developed. We also found that under low conditions of fuel moisture, which is what's critical for fire spread, of course, the models still have a long way to go. When that fuel moisture is below 10%, we can get errors, around 2-3%, and that's probably not very convenient. This is something that we will need to improve in the future, but that's where the science is right now. Values below 10% could have a 2-3% error on average. And in order to make this useful and that it doesn't stay just useful for the non-scientific community, in order to increase its operability and its applicability, we have developed a web application where you can go and tell with this cursor here, which moves, you can set the temperature and relative humidity, and it's going to tell you the vapor pressure deficit, and it's going to tell you what the value of the dead fuel moisture content is for different vegetation types, because the value is going to depend on the fuel, of course. So then, after focusing on dead fuel moisture, live fuel moisture, dead fuel moisture, we then got into the vapor saturation issue. So then we looked at the statistical distribution of vapor pressure deficit values across biomes, as well as the value of the atmospheric component, how it varied with biomes, and then we looked at the statistical thresholds associated with these large and very large fire events. So cumulative burn area on the y-axis and the hot, dry, and stable index on the x-axis. And here we can identify the different critical values. So we then tested whether these critical thresholds actually work and whether they're associated with different fire sizes. And we have developed these proxies, these thresholds, where for European territory as well as for the different biomes within Europe, we have values for a quantile 0.5, meaning fires of average size, 50%, for quantile 0.75, and for quantile 0.95. And overall, we see that the index seems to work reasonably well. Values go increasingly higher as fire sizes increase. The only issue that we had was with, and that was expected, was with biomes 5 and biomes 8. And this is because biome 8, if you remember from the previous slide, that was the grassy steppe biome, and biome 5 was the alpine biome. So that's the reason why they don't work, because they're ecosystems that rarely experience fires. Now, the good thing is that we have now this long data set for the last 20 years or whatever since MODI started, and we can then very quickly pull out analysis to identify extremes, extreme PPD days, extreme LFMC days, and so on, extreme days with very unstable atmospheric conditions. And this is an example of the 2022 fire season, but similar examples we can do with whatever comes, because now we have this database for the whole Europe. And so, so to summarize, we have developed this metric that can define what a fire day, whether we're going to have a fire day or not. We know which are the key drivers of fire activity associated with critical fire danger conditions. We have determined which is the best model for dead fuel moisture content, and we have also developed this new metric thanks to Fire EU Risk project. So thank you all for listening, and that's all from my side. Best wishes. Thanks.
Brilliant. Okay, thank you, Christina, for persevering there. I think actually when people listened on the earphones, it was okay. Oh.
Well, hopefully.
Yeah, I mean, don't worry about it. So what we'll do is, just to the audience, we'll make Victor's presentation available alongside all the others, and then you can watch it at your own leisure with some better sound. So thank you, Christina. Thank you, Angel. And I'd like to now introduce our colleague. Johanna Krantz is now going to give you some information about the fuel moisture campaign that we took part in, or did here in our part of Central Europe, and within Fire EU Risk. And this is also some of the work that Valerio was referring to earlier. So Johanna, the floor is yours. Thank you very much.
Thank you. I'm Johanna Krantz. As Chris introduced, I'm also working at the adjacent University of Technology. And I will talk about the fire weather and fuel moisture field campaign that we conducted in the past 2 years at the Central European pilot site. You've already heard about by Valerio about the fuel moisture content, that it is an important determinator for fire ignition probability and fire propagation. And as you can see in this map again, that there's quite a strong lack of data in Central Europe. And we wanted to fill a bit of a gap for the Central European study sites in 22 and 23, the past 2 years. As you've heard already, fuel moisture content is calculated by the wet and the dry mass of the vegetation. And we differentiate between live fuel moisture content and dead fuel moisture content. Dead fuels are fuels such as litter, fine and coarse woody debris, which depends mostly on meteorological conditions, while live fuels depend mostly on leaves and needles, branches or stems that still contain water and are attached to the tree. Live fuel moisture content, in contrast to dead fuel moisture content, is also dependent on meteorological conditions, but additionally also to plant traits such as plant adaptation strategies to drought and also hydrological conditions. We started the sampling in 2022 at the ICO site in Tarant, in the Tarant forest. And we climbed into the trees. We sampled on ground and in shrubs and grasses weight the sampled fuels before and after drying them in an oven for around 2 days. As you can see here, these are the first results from 2022. You can see that the dead fuel moisture content quite nicely follows the soil water content and even shows the lowest values during the time when the wildfire in the national park started. In the following year, 2023, we set up 3 additional sites, 2 more in the national park and 1 at the Forest Tarant, additionally to the ICA site. These fire weather stations comprise different sensors with a standard set of meteorological variables such as wind speed, power, temperature, and relative humidity, as well as soil moisture, and throughfall, so the rainfall that is not intercepted within the top of the canopy, and also the fuel stick moisture and temperature using these fuel sticks that represent 10-hour fuel. Additionally, we also continued sampling the fuel moisture content of dead and live fuels destructively at Tarant and the other 3 sites for 2023 in order to being able to compare it to the continuously measuring fuel stick. The fire sites we installed were comprised of one dead stand of young spruces, which died because of a bark beetle attack 2 years ago, and 2 more sites in a beach stand, in 2 beach stands where one has a bit more undergrowth than the other. For the Tarant anchor station site, for the ICA site, we also installed a fuel stick, but used the meteorological data that was available directly at the anchor station itself. We then compared the dead fuel moisture content that we sampled destructively to the fuel stick, and could see that for the beach stands, the correlation was highest with fine woody debris and also litter, which is quite expectedly because the fuel stick resembles 10-hour fuels, which are similar to fine woody debris. For the spruce stands, it's a bit different that the correlation was higher for litter and fuel stick, for the litter dead fuel moisture content. We then compared it to the fire weather index. We calculated it as well following the Canadian system with the fire weather observations for temperature, relative humidity, wind speed, and rain, and calculated from those the fuel moisture content, fuel moisture codes, and the fire behavior indices from which the fire weather index itself is calculated. In this figure are the results for the 4 sites for which we calculated these fire weather indices. And as you can see, the live and the dead spruce stands show higher fire danger levels during the dry periods. That said, that 2023 was a rather wet year in the second half of the year. But still, we have one event where even the very high fire danger level that follows the FS system was reached. This Canadian Fire Weather Index system is also implemented in the FS, the European Forest Fire Information System for fire danger rating on European scale. And we use this to also compare the regional and the local fire weather index measurements, since the FS has a quite coarse resolution of 8 kilometers, but also delivers at a daily rate. As you can see here, for the dead spruce stand, especially in the dry periods, the FS overestimates fine fuel moisture content and thus underestimates the fire danger in the dry periods. In contrast, for the beach stands, the FS mostly underestimates the fine fuel moisture contents and overestimates the fire danger. So in general, the local variability across fuel types and across small scale sites is not captured by FS. And to conclude, in order to fill the gap of the lack of fuel moisture content measurements in Central Europe, we locally monitored fuel moisture content and fire weather at 4 different sites in Germany. The fuel sticks that we installed represented the local conditions of fine fuel moisture content and the fire risk. And meteorological conditions are not able to reflect light fuel moisture content conditions, as we already saw before. And there are satellite-based modeling approaches necessary, such as the one presented by Sentinel-3. And in the end, FIS does not capture the local variability and the difference in fuel types due to its coarse resolution. I thank you for the attention and hopefully can answer some questions in the chat.
It's all yours.
Do you see my screen?
We can see your screen, yeah.
Awesome, cool. Okay, so when I talk about the wide and urban interface in the context of a fire URIS project, you have to bear in mind that we mapped the wide and urban interface across the entire continent and across 5 pilot sites, and Central Europe is one of those pilot sites. So some of the decisions which results in the patterns of the maps you see are driven by the fact that you want to compare those broad scale maps across regions. So you might find that very locally, the wide and urban interface map is not precisely what you would think, but think of it as a regional map. So, but I have to start with a definition. So the formal definition of a WUI is where settlements are interspersed within or adjacent to flammable vegetation. So we're interested in all places of human habitation, and we expand this to places where human work. So for example, factories, agricultural buildings, etc. So everywhere essentially we have buildings, and that these buildings are surrounded by some degree by vegetation that can carry fire. So why is the WUI a growing issue in fire research worldwide? Why are we so worried about the WUI? Well, this is the epicenter of human exposure and property exposure to fire risk. These are the parts of the world that tend to be disproportionately affected by the adverse effect of fires. So there's a great need to identify where they are so we can devise better management and policy ways to reduce human exposure and property exposure to fire in the WUI. But when we think about fire exposure in the WUI, we tend to divide it into 2 separate components. The first is direct exposure, and the second is indirect exposure. So direct exposure is what comes to mind intuitively. It's the case where we have buildings and settlements and villages and cities that border vegetation, and fire fronts can reach directly to the boundary of those buildings and towns and settlements and ignite them via direct heat transfer. So this is a common case. But when we map the WUI, we have to account another very, very common mechanism of home ignition in WUI areas, which is indirect exposure by flaming embers that fly well ahead of a fire front, sometimes even several kilometers. They land on the top of the buildings or in the vicinity of buildings and cause their ignitions. So even buildings and settlements that are not necessarily surrounded directly by vegetative fuels may ignite by approaching fires via spotting mechanisms. So this is what we have to account for when we find ways to map the WUI. There's also another way to think about the WUI, and very typically when you see WUI maps from different countries, they're divided into 2 separate classes of WUI, and these classes of WUI account for different types of exposure, but also different types of fire spread in the WUI. On the left-hand side, you can see what we call the intermix WUI. And the intermix WUI is the case where we have contiguous vegetation, and the buildings of the settlements are essentially located inside the vegetation. So most of the area in between neighboring houses is vegetated. And when fire spread occurs in these areas, it spreads mostly via flaming the wildland fuels. The second type of WUI is the interface WUI, which you can see on the right-hand side. In this case, we have a much clearer boundary between the settlement and the surrounding flammable vegetation. So if you think of a fire front approaching from the west to east in this picture and reaching the boundary of a settlement, it can then ignite houses in the settlement, but most of the spread of a fire inside the settlement will be by home-to-home ignition and not via vegetation, simply because there's not much vegetation inside it. So when we map the WUI, we tend to map these 2 cases separately and combine, and I'm going to show you that in a second. So how do we map the WUI? We have to make some assumptions, especially when we create broad-scale maps like the one we use here, we have to use some rules of thumb, and we have to rely on 20 years of research into WUI mapping, and we have to make some decisions. And some of these decisions might sound simplistic to you, but that's what you have to resort to when creating broad-scale maps. It's always possible to create fine-scale maps by tweaking these decisions, to specific case studies. So we first start by identifying places we call intermixed WUI. So again, intermixed WUI, where buildings are surrounded mostly by vegetation. And the rule of thumb we're applying is that any built-up area which has more than 50% vegetation, woody vegetation in our case, within a 500-meter buffer around it, is defined as intermixed WUI. As for the interface WUI, recall these are places that don't necessarily have vegetation right around the built-up areas, because we make the assumption that they can be ignited by flaming embers. So we have to account for cases where even though we don't have vegetation around the buildings, these buildings are within a certain distance, in our case 600 meters, from large patches of forest that can support potentially, under the right meteorological conditions, flaming embers that can land on these houses and ignite them. What sort of input data we need to map the WUI? And these are the examples from the Central European pilot sites we've been talking about today. So we need just two types of information. We need information about built-up areas or buildings. And in the case of your study area, we have information about the exact locations of roughly 2 million individual buildings. Now, these buildings can be houses, but they can also be industrial and agricultural buildings. So any sort of building counts, because we are measuring essentially the potential loss of property. The second type of input data we need is information about flammable vegetation. And within the context of our project, we make some assumptions. And the main assumption is that we're treating flammable vegetation as mostly being based on woody vegetation. So we ignore grasslands, even though we can add them later. And when we account for woody vegetation, we combine forest classes and shrubland classes, and we, at this stage, make no distinctions between different fuel types. This is under the assumption that given severe enough weather conditions and drought conditions, any woody species can burn and create exposure to fire to humans. So how does it work? We start with the buildings and we define any place that's within 100 meters around the building as a built-up area. So essentially buildings and the yards around them. Then we look for each built-up area, we look at a radius of 500 meters around it and ask, is there more than 50% woody vegetation? If there is, we call this wild and urban intermix, or the intermix WUI. If not, we now test if this built-up area is within 600 meters of a large patch of woody vegetation. Large, by large, I mean 5 square kilometers. If it is, we call this interface WUI. If not, this is a built-up area which is non-WUI. So when we run this across essentially the entire European territory, but in this case for Central Europe, this is what we find. How much WUI do we have? So roughly 11.6% of the boundaries of the area, within the boundaries of the area, is defined as WUI. And I'll give you context in a moment. Of this, it's roughly 40-60 differentiation or division between intermixed WUI, so again, the WUI type in which houses or buildings are surrounded by vegetation, and 60% interface WUI, so cases we have complete settlements that have clear boundaries between them and within vegetation. And if we look at differences across the 3 countries that comprise this area, we have a bit more WUI in the Czech Republic, roughly 15%, and slightly less than 10% in the German and Polish parts of the study area. This is a classic WUI map on the right-hand side. We color the intermix in red and the interface in yellow, and all the white areas have non-WUI regardless of what's in there. And you can see that the WUI varies spatially quite a bit across the area. We have regions with very high WUI and areas that don't have much WUI. Pretty much all the border areas between the 3 countries that comprise the study area have lots of WUI in them. So some context. How much is 11.62? Is it a lot? Is it not that much? So as we did this analysis for the entire European continent, in Europe, the WUI is roughly 7.4%. So the Central European study site is about 50% more WUI than the entire European territory on average. So it has WUI, but it doesn't have tons of amount compared to other pilot sites. Other pilot sites reach values of as high as 25, 30%. So it is a hotspot, but it's not a super, super high hotspot of WUI cover compared to other places. Now, in terms of the composition of a WUI in it, it's a bit different than the entire European territory. And the European territory, the split between intermix and interface WUI is closer to 50-50, whereas here it was 40-60. Now, obviously, looking at the entire study area at once, it's kind of coarse. So it might be better to do a comparison across smaller administrative zones. And to do that, we divided the study area into NUTS-free regional level zones based on Eurostats. And now we can quantify the amount of WUI within each subzone. And when you do that, you see that actually there are quite a bit of differences between these regions. For example, the Liberecki area is more than 21% WUI, so 3 times more the European average, and almost twice as more as the WUI across the entire Central European area. And this is 21.9%, it's quite a bit of WUI. So this is an actual WUI hotspot. And if we can have the Saxon Switzerland area, it has 16.7%, and the Kralovo-Hradecki area, sorry about my pronunciation, with 13.6%. But other areas have much, much lower amounts of WUI. Now, looking at WUI per area might be dependent a lot about how houses and buildings are essentially spread around the area. So a better way of looking at the WUI, or more informative in a way, is looking at buildings. So essentially what we do, we overlay the locations of buildings on the WUI area maps. And for each building, we say, is this a WUI building or a non-WUI building? And when you do that, you actually find something that's quite worrying in a way. Roughly 70% of the buildings in the entire pilot site are defined as WUI buildings. And in the Czech Republic part, we have roughly 72%. And in the German and Polish parts, we have a bit more than 60%. And if we now zoom into the Liberecki area, which you might recall has 22% WUI overall, we find that more than 90% of individual buildings in that area are defined as WUI buildings. So pretty much all of the buildings in that area are either surrounded by forests or are within a short distance, less than 600 meters of large forested area. So super high case of exposure. This is comparable to any other area in Europe. So this is like these numbers are numbers we see in southern France, we see them in Barcelona, we see them in Portugal. So this is actually a very, very stark example of high exposure. Now, just to give you a quick feel of how these things look like, here's a WUI map of the area of Stanowice, which is a village in the German part of the study area. And you can see that the village is essentially divided into 2 types of WUI. The western half of the village is marked in yellow, is bordering an agricultural area. So it has forest only on one side. So the method correctly identified it as an interface WUI. So the WUI that says we don't have vegetation from all directions. Whereas if you go to the eastern half of the village, it's colored in red. And pretty much every single house in there, every single building in there is surrounded by lots of vegetation from pretty much all directions. So this is just to give you a hunch how the method works in mapping WUI areas. Another example is what happens around the perimeter of the fire we had a couple of years ago in the Bohemian Switzerland National Park. So in here, with very few WUI areas inside the park, mostly these buildings are not necessarily places where people live. These are just, I don't know. We have most of the buildings are actually outside the boundaries of the fire, but you can see that most of the WUI near the boundaries of the perimeter of the fire is the intermix class WUI. So the high exposure type WUI. And if you go further away, larger distances away, you get more agricultural areas. And consequently, most of the WUI in them is defined as interface WUI. So the WUI that is characterized by a better distinction or boundary between vegetated areas and built-up areas. So if I summarize that, in general, this study area, this pilot site of Central Europe, has a bit higher than average amount of WUI when you compare them to the entire European continent. But if you go to sub-regions within this region, you get some places that have lots of WUI in values of WUI that are comparable to places in Southern Europe. So you have to keep that in mind. Now, two things about how you interpret those maps. As I said before, they're made based on some rules of thumb, which you might find not really suitable for your specific case, but this map, it is possible to correct or improve these maps for specific cases. You can change the parameters, tweak the parameters if you want a fine resolution WUI map. And having said that, it seems like, or it's totally possible, that some of our estimates of exposure are a bit conservative. Why are they conservative? We ignore the potential of herbaceous vegetation fuels to create fire activity. And we made an assumption that the interface WUI is defined by a 600-meter rule to account for ember travel. And 600 meter might sound like a lot, but it's actually the shortest distance out there. If you go to the very, very commonly used American approach of mapping the WUI, they use a 2.4 kilometer distance threshold. So if we apply the 2.4 kilometer distance threshold here, you'll have massive amounts of WUI. But we thought that for European cases, this number is too large. It doesn't reflect reality, so we shrunk the number a bit. Also, having said that, where at the same time we're underestimating the WUI, we are also overestimating the WUI to some degree because we lump together all fuel types, all woody fuel types into one category, which is flammable. And we do know that there are massive differences in flammability of different species. So it could be that some places that have high amounts of WUI in here actually don't have much fire exposure because they're surrounded by trees and forests that their flammability levels are actually quite low under current conditions. But bear in mind that under future potential conditions, with increasing prevalence of droughts, even species that now are not considered to be highly flammable might become more flammable. So when you think about exposure in our maps, think about the future, not about the present. And with that, I'd like to thank you. I think the WUI map, the European WUI map, is available for viewing and browsing in the Fire EU Risk Viewer, which I think you will describe later. And if you have any question, you're more than welcome to contact me at this email address. Thank you.
Okay, great stuff, Avi. Thank you for that. Can you hang around? We have a question from Slovenia, from Jascha. Would you mind answering that in the question and answers?
Yeah, sure.
Brilliant. Okay, Juan?
Okay.
Are you there?
Yes, I'll try to call share. Now.
Okay, so Juan from the University of Cordoba will now talk about the potential losses of ecosystem services affected by wildfires. Okay, over to you, Juan. You have the floor.
Okay, thank you, Chris. Now I talk about potential fire losses or fire impact using an economic point of view. The evaluation of ecosystem service is difficult, mainly in relation to landscape good, erosion, and other service. The economic evaluation is based in different equations. You can see in this slides a lot of the formulation, mathematical equation. You can read the deliverable 1.6, the base model is all information about each variable and values and different sources to find information about this. A service has an equation based on resource, the number of years without resource, price of the resource, different some variable is easy to find information, but there are other variables that is very difficult to find data in some pilot sites or countries. We can find market price of timber, grassland, and other resources, but what about soil? What about biodiversity? What about recreational resources? There are some resources that is very difficult using direct approach to calculate these values. In this sense, this is a lack of information in this pilot site about these resources, and we use other previous information of other pilot sites, such as Barcelona or Coimbra. The economic assessment of fire losses or fire impacts require 3 steps. The first is economic assessment based on the previous formulation that you can see in this slide. The second is you have a resources, you have a value, but all values you lost all values of the resources or only one part of the resources. It's necessary to know to estimate the depreciation ratio for each resources. And finally, the third step is the integration of the value of the resources that you have in a territory and this depreciation ratio. It's known as the net value chain of the resources. The University of Córdoba has different free tools. In this tool, there is one analytical tools, APPRIS is analytical, only analytical. And then, I don't know, the video is not work, but you have the possibility to have another, it's not analytical, it's graphical, and you can see the fire express because it's a fire simulator like flat mat, like other fire simulator. You can see the fire express, but then you can calculate, estimate the fire impact, the fire value in euro per hectare. You can see in this small screen the value, and the value is increasing when the fire is increasing. This is the two tools that we use to deliver the cartography of the fire risk project. In the fire risk project, you can see or you can see different resources. The first is the tangible assets, timber, tree fruit, grassland, game or hunting, and even carbon sequestration. But then there are other free, it's the free that you can see in black color that are more difficult to evaluate. Soil, biodiversity, recreational. In this case, we can adjust with other data of other pilot sites because it's impossible to get information of the Central Europe site. This is the final product of the Central Europe. You can see different color. Red is the more valued area. And you can see this is a product, not the evaluation of the natural resources. It's the vulnerability of the fire, vulnerability of the natural resources because you include the evaluation and then you include the net value chain. In other words, the fire behavior, the potential fire behavior. We use the flame length that in the fire risk task is produced with percentage. Another question that you are shown in another presentation. And then what is the future? The future is the validation. The problem is the validation of this value because you have the possibility to have information about some resources, these tangible resources. It's possible to be easy, but what about these free resources? It's very difficult to calculate or to validate this information because you can use indirect approach such as contingent valuation, travel cost measure. It's more difficult, but it's necessary to test with real fire valuation. In Spain, in the south of Spain, I test with real valuation of fire impact, and it's very similar in the south of Spain. But I don't know in the Central Euros is okay or not is okay this kind of valuation, mainly in the last one, in recreational and other resources. In this same picture, you can see this is the math of the net value chain, and you can see the net value chain, the maximum net value chain is very similar to the fire losses. That is this picture. This higher picture is fire losses, and this is net value chain. I don't know, is okay or not is okay. It's necessary to test at least tangible asset using real fight. This is the future of this pilot site and other pilot site. Thank you.
Oops. Okay, thank you, Juan. A very difficult thing to quantify, very difficult to get information for, but nonetheless, a very important subject, especially if we need to get politicians to take control of this and start to pay attention to it in terms of ecosystem services and the loss of them due to wildfire. So thank you very much for a very difficult subject. And now I'd like to hand over to Frida Plattner from RISE in Sweden. And again, this is very much related to the WURI and building safety. And we talk about factors of building survival in North European wildfires. So Frida, thank you very much for coming to talk to us, and the floor is yours.
Thank you. Do you hear me?
Yes, we hear you fine. If you just make your presentation to the full screen, we'll have
I will
everything.
make it in full screen mode. And I guess I will do it in PowerPoint here.
Yep.
Yeah. Okay, perfect.
Absolutely. Okay, all yours. Go ahead. Thank you.
Okay, thanks. So I will talk a little bit about building survivability in wildfires. And that is because within a fire area, if we look at the buildings with inside the area, all buildings are not ignited. Some buildings, like this one up to the left, they survive like green islands in a black area. And other buildings like this one, they burn down and everything around it is green. And then we have the example of these two buildings, this one and this one, where the flames actually go up to the buildings and impinge the buildings, and they may ignite or they may not. And I have looked at this from a Northern European perspective. And this idea actually comes from a couple of decades ago by a wonderful researcher named Jack Cohen at the US Forest Service, who decided to look at this more closely. And he also invented the term home ignition zone, because he saw a lot of buildings and he observed that there is a lot of difference between why buildings ignite or not. And based on his observations and of course along with all his colleagues, they made prevention programs for this type of for the type of buildings that exist in the US. And they talk about the immediate zone, the intermediate zone, and the extended zone. And that is basically easily translated: the house and the closest things to the house, the garden and the surrounding forest. And what you can do to prevent buildings from ignite within the home ignition zones. And that is, of course, again, based on the factors that makes buildings survive or not in a wildfire. Now, it would be very nice to steal Jack Cohen's research from scratch, but it's unfortunately impossible because buildings, the reason why buildings survive or not is it varies across ecoregions. So we have in Sweden, this is an example from a Swedish wildfire in 2018 in the background here. We have different sets of fuel types. And we also have different traditions when it comes to land use. And that makes our fire behavior different between different countries. And it also extends a little bit to garden vegetation. And we can have even an example within my country, Sweden. I live in the south of Sweden, where we have beech hedges almost in every garden. And this is not even possible in the north because beech doesn't survive in the north of Sweden. So of course, determining features for building loss will vary across ecoregions, and also the stuff that determines then building survivability. And another example is that in the north of Sweden, they usually park snow scooters close to the buildings. And here in the south, we don't have that much snow, so we don't have snow scooters. We may have motorcycles, but it varies still. We also have, as Avi talked about, we have different types of settlements. Here in Sweden, we have a lot of wooden facades, and I know that in the borders between the Czech Republic and Germany and so on, you have also a lot of wooden facades and similar type of buildings that we have here. It differs between countries if you have a lot of intermix or a lot of interface, and how the entire urban structure is built. And we were supposed to talk about Central Europe, but my study is unfortunately for the north of Europe. However, some of the takebacks for the north of Europe is applicable also for the Central Europe, based on that it's more closely, both fire behavior and the building types are more closely related when it comes to North Europe and Central Europe than are the more extreme Southern Europe. And these are the fires that we selected to look at the physical features for building survival in the home ignition zone in Northern Europe. We looked at 187 buildings, where 66 buildings were destroyed for 4 of the most severe wildfires in Sweden. And we looked at all the physical features that we could think of when it comes to the building, the garden, and the nearby forest. And this is one example of what we looked at. Here is one of the buildings in the Västmanland fire, and you can almost at least see that there is a wooden facade and they have a ceramic tile. And this is a very, very good photo. So if one zoom in to this picture, we can even look into the gutters and see that they have the homeowners in this specific case have cleaned their gutters this summer. We can see the garden and that it's has very sparse amount of fuel, especially close to the facade. And all of these other things, we have a mixed species type of forest here. Here is another example from the Västmanland fire, where the wind came from the northeast corner of this picture. And it passed through a 20-meter wide belt of deciduous forest before hitting this house with a wooden facade again and a ceramic tile building type of roof. And if taking all of this data through a statistical analysis, we can come up with the most significant factors for building survival in large forest fires in Sweden, which in the number 1 place comes having a lawn. And we have sometimes have no lawn or forest type of gardens. So having a lawn surrounding the building and thereby a defensible space is number one for building survival. Number two is to not store wood piles or vehicles or whatever close to the building. And number three is to have deciduous wildland vegetation around the garden. So if the forest owner or if you own the forest around the building, if you spare a few of the birch trees, you will be just fine. So we also, this analysis was based on large forest fires in the boreal area, but most buildings in Sweden are ignited in very small fires that are not accounted for by this EFIS statistics. We have approximately 125 wildfires that either threatens or ignites buildings annually. And here is a map of Sweden where the green dots, they are fires that have threatened buildings since 1996, and the red dots are the ones that have ignited buildings. So we have approximately 30 building ignitions per year, and one person also die per year from wildfires. We haven't seen a trend. It's a very short time span, of course, from 1996 to 2022. But there is no apparent trend, but we can see that this is related to spring fires. And we can also see that those wood fires are very small and they occur in meadows. And it's a matter of traditional fire use. So we have burning of grass during spring it is a tradition that dates back centuries ago. And also bonfire or open fire to burn a garden vegetation that you don't want to have is also very common in Sweden. So by clustering all of these thousands of fires that we have gathered, the wood fires, we can cluster them into typical fires that occur. And one of these is the burning of grass during springtime. And here you can even see that there is snow remaining. Another cluster or a typical fire is then the bonfire or open fire. And those also, of course, occurs during grass fire season. Another fire, which is not really accounted for by the WUI maps always, at least, is the type that's called urban vegetation fires. And it's when fires spread in vegetation, but it doesn't really care about whether it's within a city or if it's close to a forest or not. So this is a spruce hedge, and it can burn very rapidly and intensively. And in this case, the spruce hedge was ignited by, I think, a weed burner, and it destroyed this house. And it spreads the same way as in wildland vegetation, but it's still inside the urban area. And then we have the summer fires that I talked about before. So that's all for me. And I hope you can apply some of it to the Central European case.
Hi, Peter. Thank you. Thank you for that. It was Sweden, obviously, naturally, and you had slightly different problems and the springtime grassland fires. However, when we think about Avi's work earlier and just living in this region, there are plenty of places where this wildland urban interface, these types of buildings, these same things apply, and the clearing and management of vegetation and storing of flammable materials near the houses. So there's quite a number of parallels from here and from your work up there in Sweden. So thank you very much.
Thank you.
I would like to introduce Frida's colleague, Johan, and he's going to talk about spring fires. You saw it there in the chart from Frida. It's actually springland fires are a problem in Sweden. It's not just in Sweden that these springland fires occur. In Romania, through traditional land management patterns, they occur there too. And also in the Czech Republic, they also have high records of fires in the spring as well as the summer. So Johan has graciously offered to talk about the problems they have in Sweden, and maybe there's some parallels for us here in Central Europe. So Johan, the floor is yours. Thank you.
All right, excellent. First of all, do you see this screen?
We see it and we hear you. You're good to go.
Excellent. All right. We have a warning system not only for forest fires in Sweden, but we have a separate warning system and a fire danger rating for grass fires, because as you heard from Frida's talk, most fires actually occur during the spring, even though they're not as intense and large as forest fires. And they do threaten the buildings and the people in Sweden much more actually than the large forest fires. So this is the model rate of spread in northern grasslands, which we've developed, and it's operational since a few years back in Sweden. This is a typical hazardous place. Then it's just a small piece of land. This is what we call an abandoned agricultural land. It's not abandoned land. It's just that 50 years ago someone used this for either grazing or agriculture, but that's not economically viable anymore. So now it's just there. So in general, grasslands occur, they exist all over the world, right? And they actually account for 80% of the global burnt areas. And this is mostly in the savannas of Africa and South America. So we know that these fuels burn very well, but not only in the very, very dry savannas, but also in northern region. This example, it's a poor picture, unfortunately, but this example is from Colorado 2 years ago, where we had a huge fire on New Year's Eve, covering thousands of hectares and actually more than 1,000 buildings destroyed. A few hours, strong wind, and it was all over. So this example is from Sweden, and I'm going to try to see look at similarities to the Central European site. But for us, we can clearly separate two types of fires: those that occur in forest and those that occur in open land. And these are distributions of when they occur. So here is spring and here is summer, and in different regions, except for some of the islands, which are quite unusual. These are very different, right? So clearly the open land fires occur in the spring, and clearly the forest fires occur mostly in the summer. And they have a very, very different behavior. The grass fires, they can exhibit very, very high spread rates. This is Frida actually behind the flames there. We just ignited a 3-meter long line ignition, and this is, I don't know the number now, but it was like 15-20 seconds after the ignition. So very, very rapid flame spread. And also, you can have rain during the night, and there's absolutely no guarantee that you won't have rapid flame spread during the afternoon, because a few hours of low relative humidity, sunshine, and wind the grass on top of the water, which you see here, quickly dries out and can carry flames easily. And we've also seen from reading through statistics a lot, we read a lot of incident report in Frida, and that clearly people tend to underestimate the risk of fast fire spread during spring, and clearly they also seem to overestimate the rate of spread during summers. But we know that it's only the cured grass that burns. So living fresh grass, it's very, very difficult to get that to burn. But after senescence, so that is curing, so when it dies, basically, the fuel bed is instead highly flammable. And curing globally is driven by drought or high temperatures or frost. And from Central Europe and upwards, it's low temperatures during winters that kills the grass. And then after the winter, you have usually 100% cured, so dead fuel bed, where then the new grass emerge within, right? So this is an example from coastal southern Sweden, and the winters here are basically like they are in Saxony. A typical winter day, like today, we have 2 degrees, rain and wind. So by mid-March, we have completely dead fuel bed. A month later, we see some grass, some green parts in here. It's actually a lot of it if you look carefully. 3 weeks later, you see a lot of green patches little everywhere. And yet, like 12 days, the whole thing is green. If we go up further north, the spring is much shorter in time, right? So this is beginning of May up in this region here. And this is 4 weeks later, completely green. So this is highly flammable. This is completely incombustible. And you can also see how the season changes, of course, when you go up north in Sweden. So what we did was we constructed a fire danger model. And the risk index for these type of fires is rate of spread, not intensity as it is for forest fires. So we look at what affects the rate of spread, because rate of spread is what surprises people and what makes these dangerous. Well, fuel height has an effect, but we use a model system, so we don't need to map that. Fuel moisture content, we use an American model of fuel grass moisture content, but we have actually added to it new experiments for lower temperatures. So we know we have lots of fires when it's 8 degrees. So we added that, and that accounts for rain temperature, wind relative humidity, like always, but also very importantly, it's the irradiation from the sun. So we know that sunny days are a lot worse. Wind speed, that's all known, taken from experiments in Australia and North America. And then the degree of curing, which is what we've done here, basically. And this is determined from 25 years of incident statistics in this country, together with a series of burns during full seasons. So from snow melt, basically, to when the fuel cannot carry flames anymore. So we have this rate of spread. We calculate the rate of spread for a flat land fire, where we take these known rate of spreads for completely dry and completely cured grasslands. And then we decrease this with the reduction factor due to moisture content and one due to the growth of the new green grass. And this is what this looks like. So the growing days degree is, we just sum up the temperature, which is above what is a growing day, which is 2 degrees. If there's snow, nothing happens. If it's very cold, nothing happens. And then if it's a warm spring day, then this thing will increase. And when it reaches 100, the fuel can hardly support spread. So we define this in a way that it covers the whole country fairly well. And this is just an example from this region here in 2014. Not much happened during winter. It was snow, then it was cold, a bit on and off. And then about here in mid-March, fire started, and they occurred. And then all over it was no more of them from the beginning of May. And then the forest fire season started later on. Let's see, wrong way. Okay, and this is calculated in a very, very simple little algorithm that our Meteorological Institute does every day for all parts of Sweden. And then we had a number of burns of grasslands that we calculated the flame spread, and we looked at the grass and how much the grass had grown. And yeah, we could see that this is the ordinal day of, so this is basically beginning of May, and this is June. And we can clearly see that the flame spread rate decreased during the season. There's a lot of variation. Of course, since some days are dry and windy, some days are wet. So we corrected the data for that on only taking into account the actual growth of the green grass. And then we ended up with something which on a logarithmic scale is highly linear with this growing index. And so it's an exponential decrease of this growing index, which we then can just add to our model. We looked through a number of fires that we do have spread rates known to. And as always with fire, there's lots of spread, but this is a fairly well representation. Also looking at the dispatches that have occurred over the last 25 years, if we plot them onto this season index, we see that we have the exact same form, the exponential form that we had from the spread rates, only with the factor 2, which can be basically explained that just igniting the grass will probably have the same dependence on the growth of grass. And then that it spreads fast enough for the fire service to have to intervene is another one. So that gives us exactly 2 times the spread rate factor. So basically what we do is that our Meteorological Institute every day calculates this for integrated system all over Sweden. It's a 2.5 by 2.5 kilometer grid. And then for each hour in the prognosis that they have, they calculate the temperature of the grass, depending on the temperature of the air and the wind and the sun irradiation. And then they give a near fuel relative humidity based on the same quantities, and then calculate the equilibrium moisture content of the fuel. And then we calculate how the fuel moisture content will vary over the day. So based on the equilibrium moisture content and on the rain and so on, very much like the FFMC equations, but only adjusted to this type of fuel. And then we calculate the rate of spread. So we calculate the reduction due to moisture, the reduction due to the upgrowth of green grass, and then we added the wind, and then we have a rate of spread. Finally, we put these into different danger levels. So this is what we communicate to the public. If you have low, moderate, high, or very high risk of spreading grass fires. And if this is very high, this is communicated through the radio, and it's always shown in the weather reports, and of course on the Meteorological Institute's homepage. So an example, this is a typical example from May, which is to show you the variability we had in Sweden. So in the coastal south, the season is already over. So then we just say, so the grass season is ended. And then in the southeast here, we say we have a actually moderate risk. Whereas around the Stockholm area, it's a damp day, maybe some rain. So this is a very low risk. And then when you go up north, it's pretty good weather, and the season hasn't progressed that long. So it's a high risk during the north coast. And if you go further in, it's a very high risk until you reach the snow line, and the rest of the country is snow. So this is our spring reality. And this is actually the prognosis. I just took the screenshot now. This is the prognosis for this Sunday. So we have snow all over the country basically on Sunday, except for in the south, where most of the land is low risk, maybe rain, maybe very wet, and a little area where we have a high risk. So other examples is, this is just a city called Norrköping, how the moisture content during 1 month, March of 2020, varies. You can see the diurnal variation like this, and then you have rain, and then you have diurnal variations again, and then rain, and so on. And this is how the rate of spread varies then throughout this month. I actually just did a little calculation on Dresden and looking for last year. So this is 2023 data about how the season evolves. And well, it grows throughout the whole season because it's a bit warmer than here. But basically around mid-April, we would expect this grass season to be over. But then again, this is only validated in Sweden. So to apply this to Germany or Poland or Czech Republic, one would need some sort of validation, either by probing grasslands or looking at statistics. This could be easily done as long as there is statistics. So thank you for your attention. There is publications on this model also in English for anyone who is interested, and I'll be happy to answer any questions.
Thank you, Johan. I've just had to close the window because it's raining, so our fire risk grassland is all right for the moment. It's quite interesting when we sort of joined this project, and we've learned more, and we've seen these experiences from partners from across Europe. And spring grassland fires wasn't something that we'd really considered too much. However, it's not just Sweden. This year in Austria, on the Austrian-Hungarian border at the Neusiedler See, in this time, they lost 200 hectares of reeds that were dried out from the winter. Again, probably as a result of burning practice. 2020, our Polish colleagues are probably familiar with this, but 6,000 hectares of grassland were burnt on the 2nd, I just wrote it down, in April the 18th. And they lost 6,000 hectares, again, as a result of people setting fire to grass, and that was a national park. So with
probably only during a few hours, I guess.
Yeah. The one in Neusiedler was, I think, 4 hours, but the one in Poland, I think it burned for 4 to 5 days. I would have to go back, but it is a relevant subject for this part of the world, and kind of the reverse of spring grassland fires, actually the crop fires, and how they affect and how they can spread into forests, and I think that's something that needs to be further looked into. So would you, sorry, Johan, did you want to say something?
No. I'm just agreeing. I think
you agree. Oh, that's wonderful. Right. So Domingos has got a question. Maybe he doesn't agree.
No, that very good work, Juan. But one thing I'd like to comment: you are looking at the curing of grass from, let's say, from winter, spring into summer, I'd say. But in southern countries, we have also the problem at the end of the season, let's say in the end of summer, after June, July, the grass starts to dry, and then there is another cycle of, let's say, of increasing risk. I don't know if you. I recognize the importance of these early spring fires, and they are, as you said, and as Chris said, also in some other countries, for example, in the mountain regions in Italy, there is also this problem of this type of fires. But in southern Europe, I think we will face more the problem of fires in the fall of the summer season. I don't know if you are considering of looking at that. And if I may bring a question that was put this morning to Kirsten about what is the greatest problem for the houses, if it is the fires that are burned by the owners, or if it is the fires that come from outside. To this question, I was prepared, let's say, to say, at least for us in Southern Europe, we fear more the fires that come from outside because they tend to be large fires. But what I saw in your presentation makes me think that the fires that people ignite near their houses without knowing the importance of what they are doing can be also dangerous for the house and for the wild and urban interface. Okay.
Yeah, thank you, Dimos. Very valid points. Frida, would you like, Frida joined us just for a second then, when she's back. Well, some sort of ghost of Frida by the looks of it. But Frida, did you have something to say?
I really look like a ghost. It's fascinating. So I will turn off the camera.
Okay, do that.
And answer it. And you're absolutely correct, Domingos, that for the north, it's true that we are our own problem. We set fires that we cannot control, and it's our fire use that will make buildings ignite. And it's mainly a problem of the gusts that we cannot. We think that we have everything under control, and then there is a wind gust. This is very typical for the grass burning. I don't know how it is in the central of Europe, Christopher. Do you have a comment?
I think it's pretty much the same. People underestimate the danger they have when they have a fire. You can have a fire any time of year as long as it's dry enough and there are fuels and a gust comes along. There's not a lot you can do other than not have the fire in the first place. Also only have it when it's the conditions make it a little bit safer. So it is down to education and luck in some cases. So thank you very much again, Johan. Thank you for your question, Domingos, and Frida, thank you for your answer. Do we have any questions from the audience? We've come to the end of the demonstration event in terms of the products, and I'd like to give the audience the opportunity one more time to ask a question. Okay, so maybe when you've had time to digest this very, very long day and all this information, perhaps you might have some further questions about the projects or about the work that's happening here in Central Europe or any of these products. And feel free to contact me. I'll write to all you people who attended today or who registered and perhaps weren't able to attend. And we'll provide you with product cards and contact details should you require them for the people who develop these products. So I'm going to hand over now to Julia once more. And if we could just beg you for just a little bit more of your time, and then we can just go through, just see what you thought about the subjects that were just presented and these other products since lunchtime. So Julia, the floor is all yours again.
Thank you.
Thank you very much.
So just before I pose the final questions, I would like to say thank you to all of you who shared with us so many contents, so much science. And thank you so much for all the information that we gathered today. certainly we will need to kind of ingest and digest all these pieces of information. So now let me go straight and share with you my screen, first of all. Okay, is it coming? Okay, now, so again, please, I would like you to get your smartphones, and again, either type Menti, or perhaps if you have your session still open. If not, I'll wait for a few seconds for you to scan the QR on the lower left-hand corner so that you link again with the questionnaire. Still, and thank you, we are in the 42 people, which are a lot. So having your feedback is super valuable. Okay, if not, you have in the chat as well the connection numbers, which will appear in the next slide anyway. Okay, there you have the number 811-09708. So then here are our questions towards all these products that we targeted during the afternoon. So please let us know if the explanation was sufficient. And if not, in a minute, we will let you tell us what else you would have liked hearing. I think that all the subjects on the wild and urban interface were most illustrative. So we have 6 answers for the moment. Still more coming in, 8. So thank you, because this feedback also tells us that you've been very attentive to it. Yet more answers coming in. Okay, it looks like it stops there at 11. So here, a clear winner are these factors for building survivability, while the fire danger metric perhaps needs a bit more explanation. Thank you. I pass on to the next one. And here really is how suitable these products are for that Central European territory, and perhaps I would say also for the northern territories. well, 10 responses, and clearly the wildland urban interface is of concern and is highly applicable. Well, thank you for these responses also, because we are building towards a European demonstration in front of the European institutions. So the evaluation of these products will allow us also to reshape and to present what has been best and perhaps more limited, and to explain those limitations. So this is very valuable. Okay, 11 responses. So we leave it at that, and then we pass on to the next. Just to inquire in a free text manner, what other information for fire risk in the area of these products presented in the afternoon would you need? Okay, integration, detailed, recommendations, awareness, presence of people, type of construction, houses, yeah, perhaps also recommendations on constructions, risk perception, that's again integrating population. Let's see, any other suggestion? These ideas are really good, because they provide us also of the context within which we should analyze our work. Okay, then I pass on to the next one, because I don't get more responses. So how do you find, or how is the approach to fire risk products? Has it been comprehensive? Yeah, perhaps in the approach and the background used for each one of the products, we should take into consideration the algorithms and the insights of the analysis, and that might take more reading, more time to explain. So, but overall, they are very comprehensive. So I guess also the integration could be quite feasible. Okay, we have 10 answers. Let's see if we get a couple of them more. Oh, thank you. 11. Somebody perhaps is struggling with a smartphone. Let's get an extra one. Okay, we move ahead. And here we come to this double question on the usability and the interest. So on the vertical, we are saying how usable are each one of the products and how interesting in the context. Please always think of this Central European towards Nordic and Eastern Europe contexts. So if they could be ingested in the normal daily procedures. Okay, we are having a more realistic view. Nine responses. So perhaps somebody else. Here we see the dispersion of the responses. So we will analyze them later on. 11, that's good. And we're close to the end, just a couple of them more. So we would like to know some aspects, items to improve, topics. If you have any question still open, please formulate it and we'll try to respond to it also in our report to the contractor, to the commission. We will issue a summary on the whole day, the whole event. So we will address the answers, not only posed in the question and answers, but also here. Yeah, how many of these services are operational? If they are since they have been presented, is because they are operational. We have only presented in these demonstration events the fully completed products. That's a good question. We need to clarify that. Products related to the study area. So during the day, I think that we have shown the maps of the products that are available and have been tested and somehow validated over the Central European area. So most of them, if not all, perhaps Chris can say that, but we're focused on the demonstration area. Okay, how people out of the project can reach and use these products. Okay, this one perhaps is how is somehow related to the integration and access tools. And I take note also because these are topics to be raised up in our internal project meetings to make them more effective. For instance, this one, how the products can be more reachable. Okay, thank you for your questions. And now this is the very last. Just to what extent do you agree with the following sentences? So questions. And this will help us to improve the next demonstration event. So this is not directed to the products, but to the running of the session, I would say.